when we look at the vast and almost incomprehensible time span of our planet's existence, a period of 4.5 billion years, we must come to terms with the profound and humbling realization that the story of humanity is but a single, fleeting word in an immense and largely unread book. The geological record, the Earth's own memory written in layers of rock and sediment, shows us that our planet is a master of self-erasure. It is like a vast and ancient library where most of the precious volumes have crumbled to dust over the eons, where entire chapters have been torn out and rewritten, leaving only a few tantalizingly incomplete pages for us to decipher. The continuous and relentless cycle of geological processes, the slow, inexorable drift of tectonic plates, the grinding force of erosion by wind and water, the patient burial of the surface under layers of sediment, and the transformative heat and pressure of metamorphosis is constantly rewriting and reshaping the geological evidence of the deep past. With every million years that passes, another layer of our planet's history disappears into the inaccessible depths of the Earth's mantle, melted and recycled, its information lost forever. Geologists estimate that a staggering 99.9% of all of Earth's surface history is practically unknown to us, lost to the abyss of deep time. Out of the 4.5 billion years of our planet's existence, we have detailed and reliable information for only a negligible fraction of that time. Even the famous and mighty dinosaurs, who ruled the Earth for an immense period of over 150 million years, are known to us from only a few scattered and fragmented pieces of bone, a few fossilized footprints, and the occasional imprint of their skin. What then of beings that could have existed not millions, but billions of years ago? Their traces, their bones, their cities, their technologies would have long since been dissolved in the acidic waters of ancient oceans, crushed and pulverized by the slow, grinding movement of the continents, or transformed by immense heat and pressure into rocks that are now completely unrecognizable as the products of intelligent activity. When we truly try to imagine this incomprehensible chasm of time, a series of unsettling and profound questions begin to arise. What all could have happened in these vast, empty, and unrecorded eras of Earth's history? How many different forms of complex life, how many intelligent species, how many technological civilizations could have arisen and then vanished without leaving behind a single, definitive trace that we, in our modern world, would be able to recognize? Perhaps we are like a team of archaeologists who have found a single, broken shard of pottery and are now attempting to reconstruct the entire, complex, and multi-layered history of all of human civilization based on that one tiny fragment. Time changes everything, and it erases almost everything. A modern and sprawling city like London or Tokyo, with all its concrete and steel, would, after just 10 million years of erosion and geological activity, be reduced to nothing more than a thin and anomalous layer of sediment. After 100 million years, only a few strange and inexplicable mineral concentrations would remain of its existence. And after 1 billion years, there would probably be nothing at all. The planet has an enormous and almost terrifying ability to heal its own scars, to absorb the evidence of its inhabitants' activities, and to return to a state of natural wilderness. Perhaps it is precisely in this deep and profound geological amnesia that the simple answer to why we do not find the traces of ancient, pre-human civilizations lies, but some strange and tantalizing traces do remain unnatural-seeming archaeological formations that defy easy explanation. The inexplicable chemical composition of some ancient rocks, and puzzling anomalies in the distribution of certain elements that have no simple and obvious natural explanation. These deep and enduring mysteries of the geological record force us, at the very least, to consider the profound and unsettling possibility that our planet may hide a much more complex, much more ancient, and much stranger story than we have ever been able to imagine. The term Silurian Hypothesis has an interesting and somewhat whimsical origin. The name itself comes not from a dusty academic journal, but from the classic science fiction television series, Doctor Who. In the show, the Silurians were a highly advanced race of intelligent reptiles that had evolved on Earth and built a sophisticated civilization long before the emergence of humanity. In the academic world, however, this provocative and mind-bending idea was first seriously and rigorously explored by two prominent scientists, Gavin Schmidt, a climatologist and the director of the NASA Goddard Institute for Space Studies, and Adam Frank, an astrobiologist from the University of Rochester, in a paper they published in 2018. These two experts, approaching the question from their respective fields, pondered a fascinating and fundamental question: if an industrial civilization had existed on Earth in the deep, distant past, millions or even billions of years ago, would we, in the 21st century, even be able to discover that it had ever been here? Schmidt and Frank approached this question with a strict and rigorous scientific methodology. They were not trying to prove the existence of ancient, technologically advanced beings, but were instead trying to establish a set of clear and testable criteria by which we might be able to recognize the faint and subtle traces that such a civilization would leave behind in the geological record. Their work focused primarily on identifying the specific geochemical anomalies that an industrial society, similar in its scale and its impact to our own, would inevitably leave behind. They asked, how would the large-scale extraction of minerals, the widespread burning of fossil fuels, or the construction of global infrastructure manifest in the layers of rock that would survive for millions or even billions of years? The two scientists carefully and systematically analysed the various and profound traces that our own modern civilization is currently leaving on the planet: the pervasive and persistent layer of plastic materials, the unique and unmistakable signature of radioactive isotopes from nuclear testing, the dramatic and rapid changes in the chemical composition of the atmosphere and the oceans, and the large-scale redistribution of certain elements, like nitrogen and phosphorus, across the Earth's surface. All of these factors, they concluded, could potentially be detectable in the geological record even after an immense and almost unimaginable amount of time. At the same time, however, they also pointed out that many of these potential traces could be easily confused with the products of natural geological processes, or that they could be so widely and thinly dispersed over time that it would be incredibly difficult for future geologists to recognize them as the definitive and unmistakable work of intelligent beings. One of the most interesting and compelling aspects of their hypothesis is the idea that every industrial civilization, by its very nature, will inevitably have a significant and measurable impact on its planet's climate. These large-scale climate changes could be one of the most lasting and most detectable traces of such a society. The sudden and dramatic fluctuations in the concentration of greenhouse gases, such as carbon dioxide or methane, that would be preserved in the geological layers of rock or in ancient ice cores, could serve as a powerful piece of indirect evidence for the existence of beings who had learned to manipulate the chemical composition of their planet's atmosphere on a massive scale. Schmidt and Frank also pointed to a fascinating and subtle paradox that arises from this line of thinking. If such a civilization had existed in the deep past, it is highly likely that it would have used the same easily accessible energy sources that we do today. The fossil fuels that we are currently burning, the coal, oil, and natural gas, were formed over hundreds of millions of years from the buried remains of ancient organic matter. If some earlier, pre-human civilization had already discovered and depleted these finite resources, then we would not have them available to us today to power our own industrial revolution. This leads us to consider the intriguing possibility that such a society must have either existed before the formation of these fossil fuels, or that it would have had to use other, different sources of energy, and would therefore have left behind a different, and perhaps even more subtle type of geological trace. The Silurian Hypothesis, therefore, forces us to rethink not only our deep understanding of the long and complex history of our own planet, but also our own future. Are we the first intelligent species to have a profound and global impact on our planet? Or are we simply the latest in a long and forgotten line of civilizations that have risen and then fallen on this small, blue world? The geological period that occurred 2.1 billion years ago represents a key and pivotal moment in the long and dramatic history of our planet. In this ancient and distant time, the Earth was undergoing a profound and radical transformation that geologists now refer to as the Great Oxygenation Event. The atmosphere, which up until that point had been largely anoxic or poor in oxygen, began to change dramatically thanks to the revolutionary metabolic innovation of photosynthesis by primitive microscopic organisms. These tiny beings, similar to the cyanobacteria that we can still find in the oceans today, began to release vast quantities of oxygen as a waste product of their metabolism, gradually and relentlessly filling the atmosphere with this highly reactive and life-altering gas. This event completely and irrevocably changed the chemical composition of our planet and set the stage for all of the complex life that would follow. This particular epoch is extremely interesting for our consideration of the possibility of ancient, pre-human civilizations. A sufficient and stable concentration of oxygen in the atmosphere is now widely considered to be a necessary prerequisite for the emergence of larger and more complex life forms. The more complex, multicellular organisms that we are familiar with require a much more efficient way of obtaining energy than the anaerobic processes that dominated the early Earth. And it is precisely this efficiency that an oxygen-based metabolism allows. Without a well-oxygenated atmosphere, the evolution of larger and more complex animals, including the kind of intelligent beings that could build a technological civilization, would probably not have been possible. During this same period, significant geological changes were also taking place on a global scale. The great supercontinent of Columbia, which is also known as Nuna, was beginning to assemble, bringing together most of the Earth's continental landmasses. This continental rearrangement would have led to dramatic and far-reaching changes in the patterns of ocean currents and in the global climate. The surface of the Earth at that time was an almost unrecognizably different and alien landscape compared to the world we know today. The land that would one day become Europe was then part of a huge and barren landmass, surrounded by shallow but microbial, mat-filled seas. The atmosphere contained much more carbon dioxide than it does today, which means that global temperatures were likely higher and the climate was more stable. Without the dramatic and rapid fluctuations between the seasons that we are familiar with, it was also during this pivotal and transformative period that the first eukaryotic organisms are thought to have appeared. These are cells that have a true nucleus and other complex, membrane-bound organelles, and they are the fundamental building blocks of all more complex life forms, including plants, animals, fungi, and humans. This evolutionary leap from the simpler prokaryotic cells, like bacteria, to the more complex eukaryotic cells is one of the greatest and most mysterious milestones in the entire history of life on Earth. The transition to eukaryotic life enabled the subsequent emergence of multicellular organisms and opened the way to the immense and beautiful biological diversity that we see on our planet today. Some scientists have speculated that this very time, with its newly oxygenated atmosphere and its stable, warm climate, could have been a particularly suitable moment for the emergence of the first complex, and perhaps even intelligent, life forms. A stable global climate, an abundance of available energy thanks to the newly oxygenated atmosphere, and the almost complete absence of any competition in the form of other advanced and complex life forms could have created the ideal and perfect conditions for a grand and unprecedented evolutionary experiment. But could any of these primitive and early life forms have truly evolved into intelligent, tool-using beings? The traditional and widely accepted view of evolution considers this to be a highly and almost vanishingly improbable scenario. The path from the first, simple eukaryotic cells to the kind of complex and large-brained intelligence that we see in humans took more than 1.5 billion years to unfold on Earth, and it was a path that was filled with countless contingencies and random events. However, the study of evolutionary biology also teaches us that the pace of development is not always constant. Under the right set of suitable environmental conditions, some evolutionary changes can occur much more rapidly than we might expect. Moreover, we have a very limited and perhaps very biased understanding of what intelligence itself is. We do not know what an intelligence that was based on a completely different biological foundation than our own might look like, or what kind of traces it might leave behind. If we were to seriously and systematically search for the faint and subtle traces of an ancient, pre-human technological civilization, we must first have a clear and well-defined understanding of what we are actually looking for. What kind of evidence could possibly survive for billions of years, enduring the relentless and destructive forces of geological change, and still be recognizable to us as the unambiguous and definitive products of intelligent and technological activity? This question is far more complex and far more challenging than it might first appear. Most of the materials that our own modern civilization produces and relies on have a surprisingly and distressingly short lifespan on a geological timescale. The common building materials that make up our cities, such as concrete and steel, would disintegrate and crumble within a matter of thousands of years. Glass, which we think of as being very durable, would dissolve in the slightly acidic environments of soil and water over a similar timescale. Metals, even our most resistant alloys, would eventually corrode and gradually return to their more stable mineral forms. The plastics that we consider to be so durable and persistent that they now pose a major environmental problem for us would, over the course of millions of years, be broken down by heat, pressure, and microbial action into their basic chemical components. Even our most massive and most durable structures, the Great Pyramids, the massive dams, the sprawling cities, would be crushed by the immense pressure of overlying sediments or melted and recycled during the slow, inexorable process of tectonic plate subduction. It is a sobering thought that the entire physical legacy of our civilization might one day be completely and utterly erased from the face of the planet. Geologists have coined the term technosignatures to denote the specific and potentially long-lasting traces that a technological civilization could leave behind in the geological record. For a trace to be considered a true technosignature, it would have to be so distinctive and so unusual that it could be clearly and unambiguously distinguished from the products of any known natural geological processes. One potential example of such a technosignature could be the discovery of anomalous concentrations of certain chemical elements that do not naturally occur together in large quantities in nature. For example, finding a thin layer of rock that has unusually high concentrations of rare and heavy metals, such as iridium, platinum, or neodymium, in a geologically unusual and unexpected place could be a potential indicator of ancient and large-scale mining operations or some form of advanced industrial activity. Another and perhaps more promising type of technosignature could be the discovery of isotopic anomalies. Every chemical element can exist in several different isotopic forms, which have the same number of protons in their nucleus but a different number of neutrons. The ratio of these different isotopes in natural samples is usually very predictable and well understood. However, certain advanced technological processes, such as the generation of nuclear energy or the use of nuclear weapons, can significantly and permanently change the ratio of the isotopes of certain elements in a way that does not occur in nature. If we were to find a layer of ancient rock with a highly unusual and unnatural isotopic composition, it could be a powerful and compelling clue to the existence of some form of ancient technological activity. The problem, however, is that even some natural processes, such as the activity of a natural nuclear reactor, like the one found in Oklo, or the impact of a large meteorite, can sometimes create similar, though usually less pronounced, isotopic anomalies. One of the biggest and most fundamental challenges in the search for the evidence of ancient, pre-human civilizations is the difficult task of distinguishing between artificial and man-made structures and the often complex and surprisingly regular structures that can be created by purely natural processes. Nature itself can create incredibly complex, beautiful and regular structures that might, at first glance, appear to be the product of some form of intelligent design. The perfect and intricate geometries of crystals, the strange and hexagonal columns of geological formations like the Giant's Causeway in Ireland, or some of the complex and repeating patterns that can be found in sedimentary structures can all look almost like artificial and man-made creations. Conversely, the artifacts that were created by intelligent beings could, after billions of years of erosion, tectonic activity, and the transformative heat and pressure of metamorphosis, become so distorted and so weathered that they would be completely indistinguishable from the surrounding natural formations. Even if an ancient and advanced civilization had existed on our planet, it is highly likely that it would have used completely different and perhaps even unrecognizable forms of technology than we do. Perhaps their artifacts and their machines were based on fundamental physical principles that we do not yet know or understand. How would we even begin to recognize the faint and subtle remains of a technology that works on the basis of processes that are completely outside of our current scientific paradigm? It is a question that highlights the profound and perhaps insurmountable challenges of this fascinating and speculative search. One of the most remarkable and perplexing geological formations that could, at least in a speculative sense, be interpreted as a potential technosignature of an ancient and advanced civilization are the famous natural nuclear reactors that were discovered in Oklo, in the West African nation of Gabon, approximately 2 billion years ago. A series of self-sustaining natural nuclear fission reactions took place here, deep underground, in a rich deposit of uranium ore. This is a phenomenon that has no known parallel anywhere else in the world. These natural reactors are thought to have operated intermittently, in cycles, for a period of up to 1 million years, and their remarkable existence was only discovered by chance in the 1970s, when French scientists were analysing the isotopic composition of uranium that had been mined from the local area, and found it to be depleted in the fissile isotope, uranium-235. What makes these natural nuclear reactors so extraordinary and so deeply puzzling is their incredible and almost uncanny similarity to our own modern, man-made nuclear reactors. The Oklo reactors operated on the very same fundamental principle as our most advanced pressurized water reactors. The rich veins of uranium ore were surrounded and infiltrated by groundwater, which acted as a natural neutron moderator, slowing down the neutrons produced by the fission of uranium and allowing them to sustain the chain reaction. The reactions are thought to have occurred in regular cycles. As the fission reaction proceeded, the water would heat up and turn to steam, which would then escape. The loss of the water moderator would cause the nuclear reaction to slow down and stop. Then, as the reactor cooled, the water would return and the whole cycle would begin again. This remarkable self-regulating mechanism is strikingly similar to the sophisticated safety systems that we have designed and built into our own modern nuclear power plants. The strangest and most debated aspect of these ancient natural reactors is that, according to some detailed analyses of their isotopic byproducts, it is very difficult to explain how they could have operated so efficiently and so stably for such an incredibly long period of time without some form of external and intelligent regulation. Some scientific studies have suggested that the specific and precise geometric arrangement of the uranium veins and the surrounding geological environment is unusually and almost impossibly ideal for the maintaining of a controlled and sustained nuclear reaction. It is almost as if someone or something had carefully and deliberately designed these natural reactors for optimal and long-term performance. This has, of course, led to the bold and highly controversial speculation of whether these reactors might have been artificially created, or at the very least artificially modified, by a race of intelligent beings that existed on Earth 2 billion years ago. Could an ancient and advanced technological civilization have discovered and then used these natural and highly concentrated deposits of uranium as a long-term and stable source of energy? Could they have somehow modified the natural structure of these deposits to better serve their own technological needs? Or even, as some authors of more speculative and science-fictional literature have suggested, could these reactors have been a part of the vast and powerful energy infrastructure of a now long extinct and forgotten civilization? Of course, the vast majority of geologists and physicists prefer a much more conservative and a much more likely explanation. Natural processes can, on rare occasions, create structures that appear to be incredibly complex and seemingly purposeful. The unique and high concentration of uranium ore in the Oklo region could have been formed through the natural action of water passing through the surrounding rocks, which would have dissolved and then redeposited the uranium minerals in certain specific and highly concentrated layers. The cyclical and self-regulating operation of the natural reactors can be plausibly and elegantly explained by the natural and periodic changes in the local groundwater level. Nevertheless, the Oklo phenomenon remains one of the strangest, most beautiful, and most thought-provoking geological formations that has ever been discovered on our planet. These ancient and powerful natural reactors are a living and breathing proof that nature itself can create systems that are so sophisticated, so elegant, and so complex that an intelligent and highly advanced engineer could have designed them. Or perhaps they are the faint and subtle proof of something even more remarkable, something that has been lost to the deep and silent abyss of geological time. Our planet hides many other deep and profound geological mysteries that scientists are still struggling to fully and completely explain. Although there are reasonable and plausible scientific explanations for most of these strange phenomena, some of the anomalies that have been discovered continue to raise deep and difficult questions and to fuel a great deal of speculation. One such mysterious and puzzling structure is the Klondike Mountain Formation, which is located in the state of Washington in the United States. This complex geological formation contains unusually regular and repeating layers of different and distinct minerals, which some observers have compared to the regular and repeating patterns of artificial and man-made structures. Another interesting and perplexing anomaly is the existence of certain metal-rich geological layers that have been found in unusual concentrations and combinations. For example, in South Africa, there are ancient deposits of vanadium and titanium that are found in geological formations that, according to some geologists, have a very unusual and difficult to explain distribution of these particular elements. The traditional and most widely accepted explanations for these formations include various forms of volcanic activity and the complex chemical processes that can occur during the process of sedimentation. However, The detailed and specific mechanisms of their formation remain a subject of ongoing and intense research and debate. In 2016, a team of scientists in Western Australia discovered what they believe to be fossilized microbial structures that are 3.7 billion years old, which would make them some of the oldest known and most direct evidence of life that has ever been found on Earth. What is so interesting and so puzzling about these ancient structures is that they exhibit a surprising and unexpected degree of complexity for such an ancient and early period in our planet's history. Some researchers have pointed out that this could suggest that the evolution of life on our planet may have proceeded much faster in certain periods than was previously and widely thought. Other fascinating and unexplained anomalies concern the sudden and dramatic changes that have been observed in the chemical composition of certain geological layers. For example, during the end Permian extinction event, which occurred about 250 million years ago, there were dramatic and catastrophic changes in the isotopic composition of carbon that was preserved in ancient marine sediments. These changes clearly indicate a massive and rapid release of methane and carbon dioxide into the atmosphere. But the exact and ultimate source of this release remains a subject of intense and ongoing scientific debate. Unusual and highly regular structures have also been found in the ancient rocks from the Precambrian period in various different places on our planet. These strange formations sometimes contain different minerals in an arrangement that seems to be too regular and too ordered to have been formed by purely random and natural processes. However, most geologists are quick to point out that the natural and well-understood processes of crystallization and sedimentation can, on their own, create surprisingly complex and ordered structures. It is very important to emphasize that for all of these strange and puzzling anomalies, there are plausible and well-supported scientific explanations that do not require the intervention of any intelligent, technological beings. The natural and powerful processes of tectonic activity, of volcanism, of the complex chemical reactions that occur in sediments, and of the biological activity of microorganisms can all create structures that, at first glance, might seem to be too complex or too regular to have arisen by pure chance. Modern science provides us with a robust and powerful framework for understanding these deep and profound geological mysteries. However, the long and often humbling history of science itself teaches us that our current understanding of the world is never complete. There are always new and unexplained phenomena that lie just beyond the boundaries of our current knowledge. What we consider to be inexplicable today may find a simple and elegant natural explanation tomorrow, or perhaps one day, we will discover something that will completely and fundamentally change our entire view of the long and mysterious history of our planet. If a complex and advanced technological civilization had existed on our Earth billions of years ago, how long could any of the traces of its existence have possibly lasted? This is a key and fundamental question that we must ask when we are trying to assess the probability that we could ever find any definitive evidence of such a civilization today. Scientists have conducted a number of fascinating and revealing calculations that can help us to estimate the potential lifespan of various different materials and structures over the vast and almost unimaginable scales of geological time. Let's imagine for a moment a modern and sprawling city like London, or New York, or Tokyo. How long would these vast and complex metropolises last if humanity were to suddenly and completely disappear from the face of the planet? According to the best estimates, after just 1,000 years, most of the buildings in these cities would have completely collapsed due to the relentless effects of weather and decay. After 10,000 years, only a few crumbling and unrecognizable fragments would remain of the concrete and steel that once formed these towering structures. After 1,000,000 years, the slow but powerful processes of erosion would have removed almost all of the surface structures, and after a mere 10 million years, the even more powerful geological processes of sedimentation and tectonic activity would have completely and utterly reshaped the landscape, leaving behind no visible and recognizable traces of these once great cities. After 100 million years, all that would remain of our vast and sprawling cities would be a thin and almost undetectable layer of sediment that had an unusual and anomalous concentration of certain chemical elements, such as calcium from the concrete and aluminum and iron from the steel. After 1 billion years, a timescale that corresponds to the immense age of a potential Silurian civilization, there would almost certainly be no recognizable and definitive traces of our advanced technological society left at all. The scientists Peter Ward and Donald Brownlee, in their groundbreaking and influential book, Rare Earth, have calculated that after a period of 100 million years, all of the man-made constructions on our planet, including even the largest and most durable ones, like the Great Wall of China or the Great Pyramids of Egypt, would have completely and utterly disappeared from the surface of the planet, erased by the slow and patient hand of geological time. However, some of the materials that our civilization produces could potentially last much longer than others. The artifacts that are made of very resistant and non-reactive metals, such as titanium or platinum, could resist the forces of corrosion for an extremely long period of time. The radioactive waste from our nuclear power plants would leave behind a detectable and unmistakable isotopic trace for hundreds of thousands of years. Some of the synthetic materials that we have created, such as certain types of polycarbonates, could also survive for a surprisingly long time in certain specific and protected environments. But even these, our most durable creations, would eventually be crushed or melted or chemically transformed by the relentless and powerful geological processes of our planet. The best hope for the long-term survival of any of our artifacts would be for those objects that we have placed in space, or on the surface of the Moon, where there is no erosion caused by water and atmosphere. If an ancient and advanced civilization had sent satellites into orbit around the Earth, or had built durable structures on the surface of the Moon, then these could, in theory, survive for billions of years. The problem, however, is that the lunar surface is constantly and relentlessly being bombarded by a rain of tiny micrometeorites, which, over the course of billions of years, could slowly but surely disperse, or bury, or destroy even the most durable of artifacts. It seems, therefore, that the chance of ever finding any direct and unambiguous evidence of a technological civilization that is billions of years old is extremely vanishingly small. If such evidence does exist, it would most likely be very indirect and very subtle, such as the discovery of unusual and anomalous concentrations of certain elements or isotopes, which could be interpreted in many different and often contradictory ways. One of the most convincing and potentially detectable pieces of indirect evidence for the existence of an ancient, pre-human technological civilization could be the discovery of the faint and subtle traces of large-scale climate change in the deep geological record. Every industrial society, by its very nature, will inevitably and profoundly modify the environment around it, and these large-scale changes can leave behind long-lasting and potentially recognizable traces in the layers of rock and ice that preserve our planet's history. Our own modern civilization, in just 2 short centuries of the Industrial Revolution, has already significantly and perhaps irrevocably changed the atmospheric composition of the Earth. The widespread and relentless burning of fossil fuels has dramatically increased the concentration of carbon dioxide in our atmosphere, from a pre-industrial level of approximately 280 parts per million to a current level of over 400 parts per million. This dramatic and rapid increase in greenhouse gases will undoubtedly be reflected as a clear and unambiguous signal in the future geological layers of our planet. Similarly, any ancient and advanced industrial civilization would have, in all likelihood, left behind its own specific and unique climatic signature. Paleoclimatologists, the scientists who study the history of the Earth's climate, use a variety of different proxy data to reconstruct the climates of the deep past. These proxies include the isotopic composition of the ice in ancient glaciers, the chemical makeup of deep-sea sediments, and the types of fossils that are found in different geological layers. These detailed records show us that the Earth has undergone many dramatic and often catastrophic climate changes throughout its long and complex history. Some of these ancient climate events, such as the Paleocene-Eocene thermal maximum, which occurred about 55 million years ago, involved a sudden and dramatic increase in global temperatures and in the concentrations of greenhouse gases in the atmosphere. This particular event is especially interesting because it involved the rapid and massive release of a huge amount of carbon into the atmosphere, which led to a global warming of between 5 and 8 degrees Celsius over a period of just a few thousand years. Scientists are still debating the exact and ultimate cause of this massive carbon release. The most common and widely accepted explanations include the sudden and catastrophic release of methane hydrates from the deep ocean floor, or a period of extensive and prolonged volcanic activity. But what if, as the Silurian Hypothesis speculates, these ancient climate changes were the faint and subtle traces of a long-forgotten and now extinct industrial civilization? An even older and more profound climatic event, the Great Oxygenation Event, which occurred about 2.4 billion years ago, represented a dramatic and fundamental change in the very composition of our planet's atmosphere. In this case, we know with a high degree of certainty that the change was of biological origin, caused by the metabolic activity of the first photosynthetic microorganisms. But this event clearly shows us that life itself can fundamentally and radically transform an entire planet in a way that leaves behind permanent and unmistakable geological traces. Another interesting and mysterious anomaly in the Earth's climate history are the so-called snowball Earth events, which were episodes of extreme and global cooling during which almost the entire planet was covered in a thick layer of ice. These dramatic and almost unbelievable climate fluctuations are very difficult to explain by the known natural cycles alone, and they seem to require some kind of powerful and external triggering mechanism. Could a technological civilization, either intentionally or unintentionally, have triggered such a cascade of catastrophic climate changes? The key and fundamental challenge in the interpretation of these ancient and dramatic climate changes is to be able to distinguish between the effects of purely natural processes and the potential influences of some form of technological activity. The Earth has an incredibly complex and dynamic climate system, with a vast number of different feedbacks and cycles that can create dramatic and far-reaching changes, even without the intervention of any intelligent beings. The powerful forces of volcanic activity, the subtle changes in the Earth's orbit around the Sun, the slow drift of the continents, and the various and complex biological processes can all have a significant and profound effect on the global climate. Nevertheless, the paleoclimatic record provides us with a fascinating and deeply humbling look into the long and often violent history of our planet. By carefully and systematically examining these ancient and dramatic climate changes, we may one day be able to uncover some unusual and anomalous patterns that could suggest the influence of something more than just the familiar and well-understood natural processes. When we study the long and often tragic history of human civilizations, we can observe a disturbing and recurring pattern. Every great civilization, from the ancient Egyptians to the mighty Romans, seems to go through a similar and almost predictable series of phases, a period of rise and expansion, a flourishing golden age, a period of decline and instability, and then, finally, a collapse. The great Roman Empire, the sophisticated Mayan civilization, the powerful empire of Angkor Wat, the long-lived Han dynasty in China, all of these and many more have followed this seemingly universal and inevitable life cycle. Could this cyclical and often tragic nature of civilization be a general and universal principle that would also apply to a potential ancient and pre-human technological society? The archaeologist Joseph Tainter, in his groundbreaking and highly influential work, identified a single, common factor that seems to be present in most, if not all, of these civilizational collapses: the problem of increasing complexity. Civilizations, Tainter argued, evolve towards ever greater levels of complexity in order to solve the problems that they face. However, each new and more complex solution requires more and more energy and resources to maintain the system, until, eventually, the costs of maintaining this ever-increasing complexity begin to outweigh the benefits that it provides. At this critical and unavoidable point, a collapse is, paradoxically, an adaptive response, a way for the society to simplify itself and to allow for a new and less complex beginning. The historian Jared Diamond, in his famous book Collapse, has emphasized the crucial role of environmental factors in the downfall of civilizations: the depletion of vital natural resources, the degradation of the soil, the effects of climate change, and the unsustainable and short-sighted use of the local ecosystem have all contributed to the fall of many powerful and seemingly invincible empires. The tragic story of Easter Island represents a miniature and cautionary version of this scenario, where the overexploitation of the island's limited resources led to the dramatic and complete collapse of the entire society. If an ancient and advanced technological civilization had existed on our planet, it would have inevitably faced the very same and perhaps insurmountable challenges. Once it had reached a certain level of industrial and technological development, it would have inevitably begun to deplete its easily accessible resources and to pollute its surrounding environment. Without a successful and timely transition to more sustainable and long-term technologies, it could have easily reached a point where its own incredible success began to undermine the very foundations of its own existence. The physicist and ecologist Tom Murphy has pointed out that a process of exponential economic and population growth cannot continue indefinitely on a planet with finite and limited resources. No technological civilization, no matter how advanced, can escape the fundamental and inexorable laws of physics, and particularly the second law of thermodynamics, which states that the entropy or disorder of a closed system will always increase. This means that every single industrial and technological process will inevitably and unavoidably create waste and heat that must accumulate in the environment. For example, our own modern civilization is already beginning to hit the limits in the availability of some key and essential materials, such as the rare earth elements that are needed for our advanced electronic components, or the phosphates that are essential for our modern and intensive agriculture. Similar and perhaps even more severe resource limitations could have affected any technological society. Regardless of when it may have existed in the deep past, it is also entirely possible that technological civilizations may be inherently and tragically self-destructive. The very development of powerful and world-altering technologies, such as the ability to manipulate nuclear energy, the creation of self-replicating nanotechnology, or the development of a true super-intelligent artificial intelligence, brings with it a host of new and potentially catastrophic existential risks. The great astronomers Carl Sagan and Frank Drake speculated that this might be the ultimate and most depressing solution to the so-called Fermi paradox, the idea that most, and if not all, technological civilizations will inevitably create the tools of their own destruction long before they are able to colonize the stars. If an ancient and advanced civilization on our planet had gone through such a self-inflicted collapse, its complex technological infrastructure would have very quickly disappeared. The faint and subtle traces of its rise and its subsequent fall might be incredibly difficult to distinguish from the products of purely natural geological processes, especially after the passage of billions of years of erosion and tectonic activity. Yet, it might have left behind certain and specific traces, such as the sudden and dramatic changes in the geochemical composition of ancient sediments, or the unusual and anomalous concentrations of certain elements that are associated with large-scale industrial activity. When we consider the profound and fascinating possibility of ancient, pre-human civilizations, we often fall into a subtle and deeply ingrained anthropocentric error. We instinctively and almost unconsciously imagine beings that are very similar to us, beings with similar needs, with similar technologies, and with similar ways of life and thought. But if an intelligent and complex life form had existed on our Earth billions of years ago, it could have been, and likely would have been, radically and fundamentally different from us in every conceivable way. The faint and subtle biological traces of such a civilization could be just as important, and perhaps even more enduring, than any of the technological artifacts that it might have left behind. Let's imagine for a moment that an ancient and advanced civilization did not build towering skyscrapers and sprawling highways, but instead chose to develop its technology on a molecular and a biological level. Perhaps it learned to manipulate its own DNA, or the genetic material of the other organisms that it shared the planet with. Such a sophisticated and subtle form of biological engineering could have left behind some strange and puzzling traces in the long and complex evolutionary history of some of the species that exist on our planet today. These traces might manifest as unusual and difficult to explain genetic sequences, or as sudden and dramatic evolutionary leaps that seem to have no clear and obvious predecessors. Scientists do occasionally encounter so-called evolutionary anomalies, which are cases where a certain complex trait or a sophisticated biological ability appears to arise seemingly suddenly in the fossil record, without any clear and obvious evolutionary precursors. A classic and well-known example of this is the so-called Cambrian explosion, which occurred about 540 million years ago. During this relatively short and geologically brief period of time, a vast number of new and complex life forms, representing most of the major animal phyla that exist today, seem to have appeared almost out of nowhere. While there are a number of different and well-supported scientific explanations for this remarkable phenomenon, such as a rise in atmospheric oxygen levels or the evolution of new genetic toolkits, some have speculated whether it might not, at least in part, be the result of some form of ancient and large-scale biological engineering. An even older and more mysterious evolutionary event is the very origin of the eukaryotic cells, which form the fundamental basis of all complex organisms, including humans. These complex and highly organized cells are thought to have arisen about 2 billion years ago, when a simple prokaryotic cell, like a bacterium, engulfed another, smaller bacterium that later evolved into the mitochondrion, the powerhouse of all of our cells. This ancient and profoundly transformative endosymbiotic event was so incredibly improbable and so utterly revolutionary that some scientists have considered it to be one of the greatest and most mysterious single steps in the entire history of life on our planet. Could a hypothetical ancient and advanced civilization have left behind some kind of a genetic signature, a message or a marker that has managed to survive in the genomes of living organisms to this day? The molecule of DNA does decay and change over time, but some fundamental and highly conserved pieces of genetic information could be passed down from generation to generation over billions of years. For example, if these ancient beings had genetically modified some simple organisms to be better adapted to certain specific and extreme environmental conditions, then these artificial modifications could, in theory, persist in the genome of their distant and modern descendants. The great and fundamental problem with trying to identify such ancient and subtle genetic traces is that the process of natural evolution itself is capable of creating incredibly complex and sometimes very surprising structures on its own. How would we ever be able to distinguish between a product of natural adaptation and the result of some form of artificial and intelligent intervention? Moreover, after the passage of billions of years of subsequent evolution, the original and artificial genetic modifications would most likely have been so transformed and so overwritten by natural mutations that they would be completely and utterly indistinguishable from the products of natural and random genetic noise. An even more interesting and tantalizing possibility is that an ancient and long-lived civilization could have and consciously created some form of biological message, a piece of complex information that was encoded into the very fabric of DNA and was specifically designed to survive for eons. Some of the long and repetitive sequences of DNA that are found in our own genome, the so-called junk DNA, have no apparent and obvious function, and could, in theory, be used to carry such a hidden and ancient message. However, the immense challenge of trying to distinguish a meaningful and intelligent message from the vast sea of random genetic noise would be extremely difficult, if not impossible, especially if that message had been created by an intelligence that had a completely different way of thinking and a different form of logic than our own. If we were ever to find the faint and subtle biological traces of an ancient, pre-human civilization, they would most likely be very indirect, very ambiguous, and very open to a wide range of different and often contradictory interpretations. Yet, this profound and beautiful idea forces us to be humble when we are studying the long and complex history of life on our own planet. It reminds us that there may be more to the story of evolution than we currently understand. When we think about the possibility of ancient, pre-human civilizations, we often and instinctively imagine them as being similar to our own as land-based and terrestrial beings, with cognitive and sensory abilities that are similar to those of humans. But what if intelligent and complex life on Earth had first arisen in an environment that is completely and fundamentally alien to us, the deep and mysterious oceans? This idea forces us to radically and profoundly reconsider our most basic and deeply ingrained assumptions about the very nature of intelligence and the definition of a civilization. The oceans cover more than 70% of our planet's surface, and they represent the largest and most continuous habitat on Earth. In many important ways, the oceans are a much more stable and predictable environment than the land, with much smaller and more gradual temperature fluctuations, and a natural and effective protection from the harmful and damaging effects of cosmic radiation. We know that the first and most primitive forms of life on our planet originated in the oceans, and for the vast majority of Earth's long and complex history, all of the planet's biological activity was concentrated in its vast and diverse marine ecosystem. Let's imagine for a moment an intelligent and sophisticated oceanic species that had evolved in the deep and dark waters of an ancient sea. Such a being could have a completely different, and perhaps even unrecognizable type of intelligence than our own. Instead of relying primarily on the sense of sight, it might have navigated its world through the use of sophisticated echolocation, like a modern dolphin, or through the perception of the subtle and complex electrical fields that are generated by other living organisms, like a modern ray. Its cognitive and mental abilities would have been profoundly shaped by the complex and three-dimensional oceanic environment in which it lived, which could have led it to a completely different and perhaps even incomprehensible understanding of the fundamental concepts of space, time, and causality. Such an oceanic species would have faced a completely different and unique set of evolutionary pressures than the terrestrial creatures that we are familiar with. It would not have had to deal with the constant and crushing force of gravity in the same way that we do, which could have had a profound and dramatic effect on its body structure and its mode of locomotion. It almost certainly would not have discovered and developed the use of fire as a key and transformative technology, a step that is often considered to be one of the most critical and most important in the long and complex development of our own human civilization. Instead, it might have developed other, equally powerful and sophisticated technologies that were based on the subtle and precise manipulation of water currents, of sound waves, or of the complex and beautiful biological processes that surrounded it. An oceanic and intelligent species could also have created social and political structures that were very different from our own. It might have moved and lived in large and complex social groups, similar to the modern pods of dolphins or whales, with highly sophisticated and nuanced communication systems that were based on the complex modulation of sound, or it could have formed vast and interconnected colonial structures, similar to the Great Coral Reefs, where millions of individuals were physically connected to one another but were still cognitively and psychologically independent. From the perspective of the archaeological and geological record, an oceanic civilization would present an even greater and perhaps even more insurmountable challenge to detect than a terrestrial one. The ocean floor is constantly and relentlessly being renewed and recycled through the slow but powerful process of the subduction of the tectonic plates. This means that most of the ocean floor on our planet today is younger than 200 million years old. Any of the structures that might have been built on the ancient seabed would have long since been swallowed up and destroyed by these powerful and inexorable geological processes. Moreover, if an ancient oceanic civilization had used primarily biological and biodegradable materials to build its structures, instead of the more durable materials of metal or stone, then these artifacts would have decomposed and disappeared even faster. Yet even an ancient oceanic civilization could have left behind some faint and subtle traces of its existence. It might have modified the marine ecosystems in a way that would have persisted in the geological record, for example, by creating extensive and unusual reef-like structures. It could also have changed the fundamental chemical composition of the ancient oceans, for example, by regulating the content of carbon or oxygen in the water, which could be detectable as a chemical anomaly in the ancient sedimentary rocks. The profound and beautiful idea of an ancient and intelligent oceanic civilization forces us to fundamentally reconsider our deep and often unconscious understanding of what it actually means to be an intelligent being, and what truly constitutes a technological and advanced society. It broadens our view of the potential and almost infinite forms of life and intelligence that could have existed on our planet, and it reminds us how limited and how biased our current understanding of these fundamental concepts may be. In the long and often violent history of our planet, there have been several catastrophic and world-altering events that geologists now refer to as the Great Extinctions. During these devastating and often prolonged periods, a significant and often overwhelming portion of the species that were living on the planet at the time completely and utterly disappeared. The largest and most devastating of all of these events, the Permian-Triassic extinction event, which occurred about 250 million years ago, managed to wipe out almost 95% of all of the marine species and 70% of all of the terrestrial vertebrates on Earth. What if some of these ancient and mysterious mass extinctions were not caused by purely natural and random disasters, but were the unintentional and tragic consequence of the large-scale activities of an ancient and advanced technological civilization? The detailed and careful study of these mass extinction events has revealed some interesting and recurring patterns. They are often and closely associated with sudden and dramatic changes in the global geochemical cycles, and especially in the carbon cycle. The Great Permian extinction, for example, was accompanied by a massive and rapid release of carbon into the atmosphere, which led to a catastrophic and runaway global warming and a severe and widespread acidification of the oceans. We are, in fact, observing very similar and deeply troubling changes in our own world today, as a direct and undeniable result of our own human industrial activity. The famous extinction event that occurred at the end of the Cretaceous period, which brought the long and successful era of the dinosaurs to a dramatic and abrupt end about 65 million years ago, is now generally and widely attributed to the impact of a large and fast-moving asteroid. However, there are some strange and puzzling aspects of this particular extinction event that are difficult to explain by this single and catastrophic event alone. For example, some species of dinosaurs and other organisms seem to have started to disappear from the fossil record even before the asteroid impact itself, and the overall extinction event seems to have continued for a long time after it. Could this prolonged and complex ecosystem crisis have been caused by something more than just the impact of a single and large celestial body? An even older and more mysterious extinction event, the so-called Late Devonian extinction, which occurred about 360 million years ago, still remains a deep and profound mystery. During this period, about 75% of all of the species on the planet disappeared, but unlike most of the other mass extinctions, this one seems to have occurred very slowly, over a period of several million years. Scientists do not yet have a clear and definitive explanation for this long-lasting and drawn-out ecological crisis. Some of the current theories include a period of global cooling, a significant decrease in the oxygen levels in the oceans, or the rapid and widespread spread of the first land plants, which would have dramatically changed the chemical composition of the soil and, subsequently, the oceans. Let's imagine for a moment a hypothetical and cautionary scenario. A technologically advanced and powerful civilization, through its large-scale and often short-sighted activities, could have unintentionally disrupted the delicate and complex balance of the planetary cycles, leading to the gradual and then catastrophic collapse of the entire global ecosystem. The widespread and persistent pollution from their industries, the large-scale deforestation of their continents, a fundamental and irreversible change in the composition of their atmosphere, or the careless and widespread manipulation of the genetic material of other organisms could have all triggered a complex and cascading series of ecological changes with far-reaching and devastating consequences. Such profound and long-lasting changes could have persisted in the geological record long after the ultimate demise of the civilization itself. The scientists Peter Ward and Donald Brownlee have proposed the powerful and evocative concept of planetary burnout, a scenario in which certain and particularly successful evolutionary branches can consume so many of the available resources or so drastically and irrevocably change their own environment that they ultimately and inevitably cause their own extinction. In their view, this is a perfectly natural and perhaps even common process, but it could also be the direct and tragic result of some form of advanced technological activity. It is very important to emphasize that for all of the great mass extinctions that have occurred in our planet's history, there are plausible and well-supported scientific explanations that do not require the presence of any intelligent, technological beings. The powerful and often unpredictable forces of volcanic activity, the random and catastrophic impacts of asteroids, the subtle and long-term changes in the patterns of ocean circulation, or the long and cyclical climatic cycles can all cause massive and devastating ecological changes. However, the careful and detailed study of these ancient and profound extinction events helps us to better understand just how fragile and how precious the delicate balance of life on our own planet is, and how easily it can be disrupted, whether by the blind forces of natural processes or by the often short-sighted activities of intelligent beings. When we contemplate the profound and fascinating possibility of ancient, pre-human civilizations, we can use the powerful and objective tools of mathematical models and sophisticated probability analyses to try to assess just how likely or how unlikely these speculative scenarios might be. In the year 1961, the great astronomer and pioneer of the search for extraterrestrial intelligence, Frank Drake, created a now famous equation that was designed to estimate the potential number of active and communicative extraterrestrial civilizations that might exist in our own Milky Way galaxy. We can adapt the fundamental logic of this equation and apply it to the long and complex history of our own planet. The original Drake equation looked like this: n equals r star times fp times ne times fl times fi times fc times l. In this equation, n is the number of civilizations in our galaxy with which we might be able to communicate. The individual factors in the equation represent the average rate of star formation in our galaxy, the fraction of those stars that have planets, the average number of planets that can potentially support life per star that has planets, the fraction of those planets that actually go on to develop life, the fraction of those planets with life that go on to develop intelligent life, the fraction of those civilizations that develop a technology that releases detectable signs of their existence into space, and the length of time for which such civilizations release detectable signals into space. If we apply a similar and adapted line of reasoning to the long and deep history of our own Earth, we can begin to ask the question of how many times a technological and intelligent civilization could have potentially developed on our planet during the 4.5 billion years of its existence. We know that life itself seems to have arisen relatively quickly on our planet, probably more than 3.8 billion years ago. But the long and winding path from the first, simple, single-celled organisms to the kind of complex and large-brained intelligent beings that we are, took a much, much longer time. The process of evolution is, to a very large extent, a random and unpredictable one. It depends on a complex and often chaotic interplay of random genetic mutations, of large-scale environmental changes, and of the intricate and often violent interactions that occur between different species. The great paleontologist Stephen Jay Gould famously and powerfully argued that if we were able to rewind the tape of life on our planet and play it again, the result would be completely and utterly different. Perhaps, in this rerun of history, intelligence as we know it would never have evolved at all, or perhaps it would have appeared in a completely different and perhaps even unrecognizable form. On the other hand, some prominent scientists, such as the evolutionary biologist Simon Conway Morris, hold the view that the process of evolution tends to converge on certain optimal and successful solutions. For example, the complex camera-like eye has evolved independently in many different and unrelated lineages, just as the phenomenon of intelligence itself seems to have appeared independently in a number of different and diverse groups of animals, such as the primates, the octopuses, the crows, and the dolphins. This suggests that intelligence may be a particularly advantageous and powerful adaptation that is likely to evolve under the right set of environmental and evolutionary conditions. If we assume for a moment that the development of intelligence and of a subsequent technological society is not so incredibly and vanishingly improbable, then how many different opportunities has the process of evolution had to create them on our planet? The Earth has gone through several major and catastrophic mass extinction events that have effectively cleared out the dominant ecological niches and have allowed for the subsequent and often rapid development of new and different evolutionary lineages. After each of these great and world-altering extinctions, a new and different wave of evolutionary experiments could have followed, a wave that could have potentially, and perhaps even inevitably, led to the emergence of some form of intelligence. We must also consider the crucial and often overlooked factor of the availability of resources. Our own modern and global civilization is incredibly and perhaps dangerously dependent on the use of fossil fuels, which are a finite and non-renewable resource that has been slowly accumulating in the Earth's crust over hundreds of millions of years. If a previous, pre-human technological civilization had already discovered and completely depleted these easily accessible and highly energetic resources, then our own subsequent technological and industrial development might have been very different, or perhaps even completely impossible. This could provide a subtle and elegant explanation for why we do not find the obvious and widespread traces of ancient, pre-human technological societies. They might have simply and completely used up all of the easily accessible and high-density energy sources, leaving nothing for us to find or to use. A detailed Bayesian statistical analysis of this problem, which was conducted by scientists like the economist Robin Hanson, has suggested that the existence of previous and ancient technological civilizations on our Earth is, on the whole, rather improbable, but it is not, by any means, impossible. Our current and profound lack of any direct and definitive evidence for such a civilization does slightly reduce the overall probability that such civilizations ever existed. But as the great astronomer Carl Sagan often reminded us, the absence of evidence is not the same as the evidence of absence, especially when we are considering a time period that is so vast and so deep that the relentless geological processes of our planet would have had more than enough time to effectively and completely remove most, if not all, of the potential traces of their existence. Although the idea of ancient, pre-human civilizations is a fascinating and deeply thought-provoking one, the modern scientific community approaches it with a considerable and a very healthy amount of skepticism. This skeptical and cautious approach is not a manifestation of a closed-minded or a dogmatic attitude, but it represents a fundamental and essential principle of the scientific method itself. Why do most scientists consider the Silurian hypothesis to be a highly and almost vanishingly improbable scenario? And what significance does this deep-seated skepticism have for our overall understanding of the world and of our place within it? One of the main and most important principles of scientific and rational thinking is the principle that is known as Occam's razor. This is a philosophical and scientific principle that states that we should not multiply the number of entities in our explanations unnecessarily, and that the simplest and most elegant explanation that is able to account for all of the available evidence is usually the most likely one to be correct. In the case of the Silurian hypothesis, we have a vast number of strange and puzzling geological and paleontological phenomena that can be satisfactorily and elegantly explained by the known and well-understood processes of nature. To introduce a hypothetical and completely unsubstantiated ancient civilization as an explanation for these phenomena would mean adding another, and a very large, unnecessary assumption to our theories, another and equally important reason for this widespread scientific skepticism is the profound and complete absence of any direct and unambiguous evidence. Despite all of the extensive and detailed geological and paleontological research that has been conducted over the last 2 centuries, not a single and definitive artifact or structure has yet been found that would unequivocally and unmistakably point to the existence of an intelligent and advanced technological civilization in the deep and distant past of our planet. Scientists, by their very nature and training, work with observed and verifiable facts and data, and without any concrete and tangible evidence to support it, it is very difficult for the scientific community to take such a radical and far-reaching hypothesis seriously. From the perspective of modern evolutionary biology, it is also a very problematic and difficult question of how a highly intelligent and large-brained being, similar in its cognitive abilities to a modern human, could have evolved in the very different and often much harsher environmental conditions of the ancient Earth. Human intelligence is the unique and complex result of a very specific and contingent evolutionary history. A history that has involved a whole host of different and often random adaptations to a very specific set of environmental conditions. It is not at all clear whether similar and suitable conditions have ever existed in the deep past of our planet, or whether, if they had existed, they would have led to the same and very specific evolutionary result. The geologist Donald Prothero has pointed out that many of the geological anomalies that are sometimes interpreted by some as being the potential traces of ancient, pre-human civilizations have perfectly well documented and well understood natural explanations. For example, the famous and remarkable natural nuclear reactors that were found in Oklo are now widely understood to be the unique and beautiful result of a very specific and highly unusual combination of purely natural geological and hydrological conditions, and they are not, as some have speculated, the definitive evidence of some form of ancient and advanced nuclear technology. Nevertheless, the practice of scientific skepticism itself has its own and very important limits. The long and often surprising history of science is filled with many famous and well-known examples of widely and dogmatically accepted theories that were later completely and utterly overturned by new and unexpected discoveries. The geocentric model of the universe, the idea of the immutability and the permanence of the continents, or the widespread and long-held belief that no stones can ever fall from the sky, all of these, and many more once prevailing and widely accepted views, were later completely and utterly refuted by new and more accurate evidence. Science progresses precisely by constantly and rigorously questioning our most established and most cherished ideas, and by actively and diligently searching for new and contradictory evidence. Healthy and productive scientific skepticism, therefore, does not mean a dogmatic and unthinking rejection of new and unconventional ideas, but rather a constant and unwavering openness to new evidence, and a deep and abiding willingness to change one's own mind in the bright and revealing light of new and more accurate information. The scientists like Gavin Schmidt and Adam Frank, who formally and rigorously introduced the Silurian Hypothesis to the scientific community, do not, in fact, claim that ancient and advanced civilizations ever existed on our planet. Rather, they are calling for a more systematic and a more rigorous examination of what kind of traces such a civilization might have left behind, and how we, in the modern era, could possibly detect them. This kind of speculative, but strictly and rigorously scientific, thinking has its own and very important value. It allows us to explore the very limits of our current knowledge, to identify the potential gaps and the blind spots in our own understanding, and to propose new and exciting research directions that could lead to unexpected and profound discoveries. Even if the Silurian hypothesis is, in the end, likely to be incorrect, the very process of carefully and systematically examining it can lead us to new and profound insights into the deep and complex geological history of our own planet, and into the inherent and perhaps unavoidable limitations of our own methods for studying the deep and distant past. Let's imagine for a moment, in a flight of speculative fancy, that we were to actually and definitively discover the unambiguous and irrefutable evidence of an ancient and advanced technological civilization, a civilization that had preceded our own humanity by billions of years. How would such a profound and world-altering discovery change our fundamental understanding of the world and of our own unique place within it? What would be the far-reaching social, the deep philosophical, and the profound existential consequences of such a paradigm-shattering revelation? The first and most obvious consequence of such a discovery would be the complete and utter end of our long-held and deeply cherished sense of our own uniqueness. Humanity has, for a very long time, considered its own remarkable intelligence and its powerful technological prowess to be something truly special, something that fundamentally and irrevocably sets us apart from all of the other and less intelligent creatures on our planet. The discovery that we are, in fact, only the second, or the third, or perhaps even the 10th intelligent and technological civilization to have arisen on this small blue planet would significantly and permanently change our perception of our own and often vaunted exceptionalism. It would be a profound and deeply humbling shift in our collective thinking, a shift that would be similar in its scale and in its impact to the Copernican revolution, which revealed to us that the Earth is not the centre of the universe, or to Darwin's great theory of evolution, which showed us that humans are not a special and divine creation, but are an integral and continuous part of the great and beautiful web of life. From a psychological and an emotional perspective, such a profound and world-altering discovery could cause a widespread and deeply unsettling feeling that the philosopher Glenn Albrecht has termed solastalgia. This is a feeling of nostalgia, of homesickness, or of a profound sense of loss for a home that one has not yet left. A feeling that arises when one's familiar and beloved environment is undergoing a fundamental and often negative transformation. Our most basic and deeply held understanding of our home, of our planet, and of its long and complex history would be radically and irrevocably altered. Our entire collective and cultural story of who we are and of where we come from would have to be completely and fundamentally rewritten. Philosophically, this discovery could lead to a much deeper and a much more urgent reflection on the potentially cyclical and often tragic nature of civilizations. If one advanced and technological society had arisen and then fallen, and then another had done the same, and now here we are, does this mean that there is some larger and perhaps unavoidable rhythm or pattern in the evolution of intelligence itself? Is the inexorable rise and the subsequent and often catastrophic fall of civilizations as inevitable and as natural as the life and death cycle of an individual organism? And what, then, does this mean for our own future? If an ancient and advanced civilization had perished due to an environmental catastrophe that it had caused itself, it would serve as a powerful and deeply cautionary tale for our own modern civilization. We might see in their long-forgotten and tragic fate a possible and deeply disturbing image of our own not-too-distant future. If we do not quickly and fundamentally change our own relationship with our planet, on the other hand, if this ancient civilization had perished due to some external and unavoidable catastrophe, like a massive asteroid impact, then this might motivate us to develop more advanced and more powerful technologies to avert similar and potentially civilization-ending threats. From an ethical and a moral perspective, a whole new and complex set of questions would also be opened up about our own relationship with any potential future civilizations. If we are indeed just one small part of a long and ancient chain of intelligent beings on this planet, then do we have some kind of a moral and ethical responsibility towards those who will inevitably come after us? Should we be actively and consciously trying to leave behind some clear and unambiguous traces of our own existence, as a kind of a message in a bottle for any future intelligent creatures that might arise? And what should be the fundamental content of such a long-term and profound message? The discovery of an ancient and pre-human civilization could also fundamentally and completely change our understanding of the nature of time and of history itself. 4.5 billion years is an almost unimaginably vast and deep time span. When we are forced to consider a civilization that may be billions of years old, we are forced to confront the immense and almost incomprehensible timescales on which the long and complex history of our planet unfolds, and the relative and almost insignificant brevity of our own human existence in this grand and cosmic context. Last but not least, such a profound and world-altering discovery could also completely change our view on the possibility of the existence of extraterrestrial life. If intelligence and a subsequent technological society have evolved on our own Earth multiple times, independently of each other, then this would dramatically and significantly increase the overall probability that a similar and independent process could have also occurred on many of the other and potentially habitable planets that we are now discovering throughout our galaxy. Paradoxically, the discovery of an ancient and long-lost terrestrial civilization could be the very thing that would strengthen our belief that we are not, in fact, alone in the vast and silent universe. While the Silurian Hypothesis remains a highly speculative and deeply thought-provoking idea, it has managed to inspire a number of new and exciting scientific projects that are aimed at actively and systematically searching for the potential and subtle traces of ancient, pre-human civilizations. These innovative and often interdisciplinary research efforts are beginning to use some of the most modern and most sophisticated methods and technologies to explore the deep and ancient geological record of our planet from a completely new and unconventional angle. Let's take a closer look at some of these fascinating and pioneering scientific endeavors. One promising and powerful approach focuses on the detailed and precise detection of any potential anomalies in the isotopic composition of ancient rocks. Every chemical element that we know of can exist in several different and stable isotopic forms, which have the same number of protons in their nucleus, but a different number of neutrons. The natural ratio of these different isotopes in the various samples that we find in nature is usually very predictable and very well understood. However, some specific and advanced technological processes, such as the generation of nuclear energy or the use of nuclear weapons, can significantly and permanently change these natural isotopic ratios in a way that is very unlikely to occur in nature. By using highly sensitive instruments like mass spectrometers, scientists are now able to analyze the isotopic composition of very old rocks with an incredible degree of precision, searching for any unusual and telltale isotopic ratios that might indicate the presence of some form of ancient and advanced technological activity. Another and equally promising line of research is focusing on the detection of anomalous and unusual concentrations of certain chemical elements in the ancient sedimentary layers of our planet. Our own modern and global civilization is currently moving huge and almost unbelievable amounts of various materials from their natural and underground deposits, and is concentrating them in new and often unnatural ways on the surface of the planet. We are constantly mining for rare and valuable metals, we are creating new and complex alloys, and we are building our vast and sprawling cities from a whole host of different materials that would not normally occur together in such high concentrations in nature. This massive and global-scale rearrangement of the chemical elements could leave behind a very specific and a very detectable trace in the geological record, a trace that could persist even after the passage of millions or even billions of years. Scientists are also beginning to study the ancient and often dramatic climate changes of our planet with a new and more open-minded perspective. By using a variety of different proxy data, such as the chemical composition of the air that is trapped in ancient ice cores, the detailed analysis of deep-sea sediments, and the study of the types of fossils that are found in different geological layers, they are able to reconstruct the long and complex history of the Earth's climate deep into the distant past. The discovery of any sudden and dramatic changes in the concentration of greenhouse gases or of other and more unusual atmospheric components could now be examined not only as the result of purely natural and geological phenomena, but also as the potential and tantalizing consequence of some form of large-scale technological activity. Paleontologists and evolutionary biologists are also beginning to study the long and complex history of life on our planet. With a more open and a more speculative mind, they are actively searching for and identifying any periods of unusually and inexplicably rapid evolutionary change, or the sudden and unexpected appearance of unusual and highly complex biological adaptations that could, at least in theory, be the result of some form of ancient and sophisticated biological engineering. Although there are currently well-supported and perfectly plausible natural explanations for most of these strange and puzzling phenomena, some of the most profound and most important evolutionary transitions in the history of life on our planet, such as the very origin of the complex eukaryotic cells, still remain, at least in part, deeply and profoundly mysterious. Interdisciplinary teams of scientists, which are composed of geologists, chemists, biologists, and even astrophysicists, are also beginning to try to model what kind of faint and subtle traces different and hypothetical types of ancient civilizations might have left behind in the geological record. By carefully and systematically comparing the predictions of these sophisticated and complex models with the real and observed data that we have, they can begin to systematically and rigorously test the various different aspects of the Silurian Hypothesis. Although the results of these pioneering and exciting research projects have not yet provided any definitive and conclusive evidence for the existence of ancient, pre-human civilizations, this very process of careful and systematic examination is helping us to better understand just how profoundly and how rapidly our own human activity is currently changing our planet, and what kind of a long-lasting and potentially permanent trace we ourselves are leaving behind for the distant and uncertain future. These innovative and forward-thinking research projects are facing a number of significant and perhaps even insurmountable challenges. The geological record of our planet is, by its very nature, incredibly and frustratingly incomplete. A vast number of the ancient geological layers have been lost over the eons due to the relentless and powerful forces of erosion, or have been completely and utterly destroyed by the slow and inexorable process of tectonic activity. Moreover, the further back in time that we try to go, the less and less of the available and reliable data that we have to work with. And yet, every single new and unexpected discovery, every strange and puzzling anomaly that we find that requires a new and better explanation, is pushing our fundamental understanding of the long and complex history of our planet forward. Even though the vast majority of scientists still consider the existence of ancient and advanced technological civilizations on our planet to be a highly and almost vanishingly improbable scenario, the very process of rigorously and scientifically testing this profound and fascinating hypothesis has a great and undeniable scientific value. It is forcing us to fundamentally reconsider our most basic and deeply held assumptions, to improve and to refine our scientific methods, and to expand and to deepen our overall understanding of the vast and almost unimaginable depths of our planet's geological history. And who knows, perhaps one day, in the course of this strange and beautiful search, we will find something truly and utterly unexpected, something that will completely and fundamentally change our entire view of the long and mysterious history of life on this small and precious planet. Whether any ancient and advanced civilizations ever existed on our planet or not, the very act of contemplating this profound and fascinating possibility forces us to think more deeply and more seriously about our own and perhaps very fleeting legacy. What will we, as a species and as a civilization, leave behind for any future and perhaps non-human beings who might one day explore the thin and fragile geological layers that contain the faint and subtle traces of our own brief and turbulent existence? How can we, in our own time, ensure that our own unique and complex story is not completely and utterly erased by the relentless and unforgiving passage of deep geological time? Some of the creations of our modern human civilization do, in fact, have the potential to last for an exceptionally and perhaps even disturbingly long period of time. The vast and almost unbelievable quantities of tiny plastic particles that we have managed to scatter all over our planet, from the highest mountains to the deepest oceans, will almost certainly form a distinct and globally recognizable geological layer, a layer that will be easily identifiable even in millions of years. The unique and unmistakable radioactive isotopes that have been produced by our nuclear tests and our nuclear power plants will also be clearly and easily detectable for tens or even hundreds of thousands of years. The massive and unprecedented transfer of carbon from the deep underground reservoirs of fossil fuels to our planet's atmosphere will leave behind a clear and indelible trace in the isotopic composition of the sediments that will persist for eons to come. But all of these unintentional and often destructive traces are more of a messy and unfortunate byproduct of our large-scale industrial activity than a deliberate and conscious message to the future. What if we, as a civilization, wanted to consciously and deliberately try to communicate with the intelligent beings of the distant future? How could we possibly hope to bridge the immense and almost unimaginable gap of deep to geological time and to leave behind a clear and understandable message that would be decipherable even after the passage of millions or even billions of years? There are a number of remarkable and inspiring projects that are currently attempting to do just that. The Long Now Foundation, for example, is in the process of building a monumental and beautiful mechanical clock deep inside a mountain in Nevada, a clock that has been designed to operate and to keep time for a period of 10,000 years. This great and symbolic clock is intended to be a powerful and enduring symbol of the importance of long-term thinking, and a profound and humbling reminder to the generations of the future that we, in our time, thought of them. Similarly, the Clock of the Long Now project, which was originally designed by the brilliant computer scientist Danny Hillis, aims to create a complex and beautiful device that will be able to measure the passage of time for tens of thousands of years. Even more ambitious are the ongoing and innovative efforts to create permanent and long-lasting archives of our human knowledge. The Arch Mission Foundation, for example, has developed a series of small, durable nickel discs that are capable of storing a vast amount of information for a period of up to 1 million years. The ambitious Memory of Mankind project is currently in the process of storing a vast and diverse collection of microfilms, which contain a great deal of our human knowledge, in geologically stable and protected locations all around the world. And the remarkable Rosetta Project is trying to create a kind of modern-day time capsule of all of the known human languages, a capsule that would be understandable even to the intelligent beings of the far and distant future. What should be the fundamental and essential content of such a profound and long-lasting message? Perhaps it should be a simple and clear warning about the dangerous and long-lasting nature of the places where we have stored our nuclear waste. Perhaps it should contain some of our most basic and most important scientific knowledge, a kind of a starter kit that could help a future and emerging civilization to avoid some of the most dangerous and most costly mistakes that we have made. Or perhaps it should be just a simple and beautiful message, a message that says that we were here, that we thought, that we felt, that we loved, and that we dreamed, just like you who are now reading this ancient and mysterious message. It is a fascinating and deeply humbling thought to imagine that some intelligent being of the distant future might one day carefully and meticulously examine the thin and fragile layer of rock that contains the faint and subtle traces of our own and perhaps long-forgotten civilization. Just as we are now trying to examine the ancient and mysterious geological epochs of our own planet, will they have enough knowledge and enough wisdom to be able to recognize our strange and often contradictory artifacts as the products of a once great and intelligent species? Or will we be as much of a deep and profound mystery to them as some of the strange and puzzling geological anomalies are to us today? Perhaps it is a great and eternal cycle that is constantly and forever repeating itself. Perhaps every single intelligent and technological civilization that arises on this planet will eventually and inevitably disappear, leaving behind only the faintest and most subtle traces of its own brief and often turbulent existence. And perhaps every new and emerging civilization will then speculate about the nature of those who might have come before it, without ever being able to gain a true and definitive sense of certainty. It is like passing a fragile and flickering torch in a great and cosmic relay race, a race where each and every runner does not know about those who have run before them, and cannot ever hope to see those who will come after them. One thing, however, is certain. Whether we are the first or the last, or just one in a long and forgotten line of intelligent beings on this small and precious planet, we are an integral and a beautiful part of something that is much, much larger than ourselves. We are a part of the magnificent and ongoing story of life, a story that has been slowly and beautifully unfolding for billions of years, and a story that will continue long after our own and perhaps all too brief civilization has finally and completely disappeared into the deep and silent abyss of time.
What if the moment you are living right now, this very second, is not a fleeting point on a line, but a place? A place as real and enduring as the ground beneath your feet. We feel time as a current, a relentless river pulling us from a past we can no longer touch toward a future that does not yet exist. But what if that feeling, as fundamental as it is the grandest illusion our minds have ever conceived? You have felt it, haven't you? A single minute spent in fear or anticipation stretching into an eternity, while an hour of joy dissolves in the blink of an eye. This is our first clue. Our brains are not passive clocks ticking off an objective reality. They are active storytellers. The prefrontal cortex, the cerebellum, the basal ganglia. These are the neural architects that build our sense of duration, sequence, and flow. When we encounter something new or dangerous, the brain records more data, stretching the moment in our memory, giving us the sensation that time has slowed. During routine, it conserves energy, and entire days can blur into a single, compressed memory. What we call the past is not a perfect recording stored in a vault, but a narrative, rewritten every time we recall it. Each act of remembering is an act of creation, where emotions from the present can bleed into the colors of yesterday. This is not a flaw in our design, it is its very nature. Our memory is not a pristine archive, but a living map, constantly updated to help us navigate the future. This realization forces a profound question. If our internal experience of time is so flexible, so subjective, what is happening in the world outside our minds? For centuries, we believed in Isaac Newton's vision of time, a universal clock, ticking at the same rate for everyone and everything, an invisible drumbeat to which the entire cosmos marched in unison. But others, like the philosopher Leibniz, argued that time wasn't a container, It was merely the order of events, the relationship between one thing happening after another. The debate remained philosophical until a young patent clerk named Albert Einstein dismantled the universal clock forever. With his theories of relativity, he demonstrated that time is not absolute. It is a local, personal phenomenon. The faster you move through space, the slower you move through time relative to a stationary observer. This is not a trick of perception, it is a physical fact, proven with atomic clocks on fast-moving jets and satellites, ticking measurably slower than their counterparts on Earth. With his general theory, Einstein revealed an even deeper truth. Gravity itself warps the very fabric of space-time. Near a massive object like a black hole, the gravitational pull is so immense that time slows to a near standstill. An astronaut hovering near its edge for a few hours could return to their ship to find that centuries had passed for their crewmates. They would not have traveled to the future, they would have simply waited for it to arrive. This reveals that space and time are not separate arenas, but a single four-dimensional continuum that can be bent, stretched, and twisted by mass and energy. If time is this malleable, a dimension that can be warped, does it have to flow in only one direction? The fundamental laws of physics, from Newton's mechanics to Schrödinger's quantum equation, are strangely ambivalent about this. They work just as well running backward as they do forward. The equations don't distinguish between a glass falling and shattering, and the shards flying back together to reform the glass. Yet, in our world, glasses only ever break. This one-way street, this arrow of time, seems to be governed by a single powerful principle, the second law of thermodynamics. It states that in a closed system, entropy, a measure of disorder, always increases. The universe began in a state of incredibly low entropy, highly ordered and concentrated, and has been moving toward greater disorder ever since. A pristine egg is an ordered system. Scrambled, it is disordered. The universe, in a sense, is constantly scrambling itself. Our memory works in the same direction. We remember the past but not the future because the act of forming a memory itself increases the overall entropy of the universe. The flow of time, then, may not be a fundamental property of reality, but a statistical trend, an emergent consequence of the universe's journey from order to chaos. This one-way flow makes the past seem immutable, a fixed landscape we have left behind. But what if we could somehow bypass this thermodynamic arrow? What if we could turn around? This is the dream of time travel, and it immediately confronts us with its most famous logical trap, the grandfather paradox. Imagine you build a machine, travel back 70 years, and prevent your grandfather from ever meeting your grandmother. As a result, your parent is never born, and therefore, you are never born. But if you were never born, who traveled back in time to begin with? The very act of succeeding erases the reason for the act itself. To escape this logical vortex, physics offers two extraordinary, though unproven, escape hatches. The first is the multiverse theory. In this view, when you travel back and alter an event, you don't change your own past. Instead, you splinter reality, creating a new, parallel universe where events unfold differently. Your original timeline remains intact, untouched, but you are now an orphan of time, forever marooned in a history that is not your own. The second idea is the principle of self-consistency, which proposes that the universe itself is paradox-proof. The laws of physics would conspire to prevent you from changing the past. The gun would jam. You would have a change of heart. A passing car would distract you at the critical moment. In this model, you can travel to the past, but you cannot change it because your actions were already part of the history that led to your existence. You are not an editor of history, but a character in a script that has already been written, playing a part you never knew you had. The quantum world, however, suggests that reality might be even stranger than a branching river or a fixed script. At the subatomic level, particles can exist in a state of superposition, occupying multiple states at once. In the famous thought experiment, Schrödinger's cat is both dead and alive until the box is opened and a measurement is made. Could time itself exist in such a superposition? Could an event be both in the past and the future until it is observed? This would mean that traveling through time isn't like moving along a line, but more like choosing a state from a cloud of possibilities. You wouldn't be changing a fixed past, but rather collapsing the wave function of history, deciding which of many potential pasts becomes the one that truly happened. This idea finds a mysterious echo in quantum entanglement, what Einstein called spooky action at a distance. Two entangled particles can be separated by billions of light years, yet a measurement of one instantly influences the state of the other. This connection appears to defy the cosmic speed limit, the speed of light, and challenges our notion of sequence. If information between them is not bound by time, it suggests that at some fundamental level, the universe is a single interconnected system where past and future are not distant points but parts of a whole that exists simultaneously. This brings us to the most mind-bending of all models, the block universe. Born from relativity, it suggests that all of time past, present, and future exists at once. As a single, four-dimensional block of space-time, time does not flow. It simply is. Our consciousness is like a spotlight moving across this block, illuminating one moment at a time, creating the illusion of passage. In this frozen reality, the dinosaurs are not gone. They are just in a different part of the block. Your future already exists. You are simply not there yet. If this is true, is free will an illusion? Is every choice we make already etched into the fabric of space-time, a frame in a film reel that already sits complete in its canister quantum mechanics, with its inherent probabilities, seems to push back against this rigid determinism, suggesting the future is not a single line but a branching tree of possibilities. Yet, the question of a pre-written destiny haunts us. Throughout history, people have claimed to have premonitions, to see glimpses of events yet to come. Neuroscience might explain this as the subconscious mind piecing together subtle clues that the conscious mind misses. But if time is not strictly linear, could these be leaks from another part of the block? Faint signals from a future that is already real. Some theories even speculate that if we are living in a sophisticated computer simulation created by a more advanced civilization, then our past would not be a physical reality at all, but a data record. And any data record can be accessed, edited, or rewound. In such a universe, the past is not immutable rock, it is malleable code. To rewrite that code, however, would require a technology far beyond our grasp, one that could perhaps manipulate closed time-like curves, theoretical loops in space-time, or harness hypothetical particles called tachyons that are born moving faster than light. But even to send a simple message to the past, a warning or a piece of advice, would be to play God with the timeline. And this is where the scientific inquiry collides with a profound ethical abyss. If you could go back and prevent a great tragedy, a war, a disaster, you might save millions. But you would also erase the world that grew from its ashes. You would erase the people who were born in its aftermath, the art created from its sorrow, a new era in astrophysics. The information provided by James Webb reveals how a major change in the universe began when galaxies collided with each other. These findings, which prove that order in the universe sometimes arises from chaos, present an extremely impressive picture not only scientifically but also cosmologically. This one-way flow makes the past seem immutable, a fixed landscape we have left behind. But what if we could somehow bypass this thermodynamic arrow? What if we could turn around? This is the dream of time travel, and it immediately confronts us with its most famous logical trap, the grandfather paradox. Imagine you build a machine, travel back 70 years, and prevent your grandfather from ever meeting your grandmother. As a result, your parent is never born, and therefore, you are never born. But if you were never born, who traveled back in time to begin with? The very act of succeeding erases the reason for the act itself. To escape this logical vortex, physics offers two extraordinary, though unproven, escape hatches. The first is the multiverse theory. In this view, when you travel back and alter an event, you don't change your own past. Instead, you splinter reality, creating a new, parallel universe where events unfold differently. Your original timeline remains intact, untouched, but you are now an orphan of time, forever marooned in a history that is not your own. The second idea is the principle of self-consistency, which proposes that the universe itself is paradox-proof. The laws of physics would conspire to prevent you from changing the past. The gun would jam, you would have a change of heart, a passing car would distract you at the critical moment. In this model, you can travel to the past, but you cannot change it because your actions were already part of the history that led to your existence. You are not an editor of history, but a character in a script that has already been written, playing a part you never knew you had. The quantum world, however, suggests that reality might be even stranger than a branching river or a fixed script. At the subatomic level, particles can exist in a state of superposition, occupying multiple states at once. In the famous thought experiment, Schrödinger's cat is both dead and alive until the box is opened and a measurement is made. Could time itself exist in such a superposition? Could an event be both in the past and the future until it is observed? This would mean that traveling through time isn't like moving along a line, but more like choosing a state from a cloud of possibilities. You wouldn't be changing a fixed past, but rather collapsing the wave function of history, deciding which of many potential pasts becomes the one that truly happened. This idea finds a mysterious echo in quantum entanglement, what Einstein called spooky action at a distance. Two entangled particles can be separated by billions of light years, yet a measurement of one instantly influences the state of the other. This connection appears to defy the cosmic speed limit, the speed of light, and challenges our notion of sequence. If information between them is not bound by time, it suggests that at some fundamental level, the universe is a single, interconnected system where past and future are not distant points but parts of a whole that exists simultaneously. This brings us to the most mind-bending of all models, the block universe. Born from relativity, it suggests that all of time past, present, and future exists at once, as a single, four-dimensional block of space-time. Time does not flow, it simply is. Our consciousness is like a spotlight moving across this block, illuminating one moment at a time, creating the illusion of passage. In this frozen reality, the dinosaurs are not gone, they are just in a different part of the block. Your future already exists. You are simply not there yet. If this is true, is free will an illusion? Is every choice we make already etched into the fabric of space-time, a frame in a film reel that already sits complete in its canister quantum mechanics, with its inherent probabilities, seems to push back against this rigid determinism, suggesting the future is not a single line but a branching tree of possibilities. Yet, the question of a pre-written destiny haunts us. Throughout history, people have claimed to have premonitions, to see glimpses of events yet to come. Neuroscience might explain this as the subconscious mind piecing together subtle clues that the conscious mind misses. But if time is not strictly linear, could these be leaks from another part of the block, faint signals from a future that is already real? Some theories even speculate that if we are living in a sophisticated computer simulation created by a more advanced civilization, then our past would not be a physical reality at all, but a data record. And any data record can be accessed, edited, or rewound. In such a universe, the past is not immutable rock, it is malleable code. To rewrite that code, however, would require a technology far beyond our grasp, one that could perhaps manipulate closed time-like curves, theoretical loops in space-time, or harness hypothetical particles called tachyons that are born moving faster than light. But even to send a simple message to the past, a warning or a piece of advice, would be to play God with the timeline. And this is where the scientific inquiry collides with a profound ethical abyss. If you could go back and prevent a great tragedy, a war, a disaster, you might save millions. But you would also erase the world that grew from its ashes. You would erase the people who were born in its aftermath, the art created from its sorrow, the wisdom learned from its mistakes. Would the new world truly be better, or just different? Changing the past isn't just a physical intervention, it's an ontological one. You would be wielding the power to unmake realities, to silence histories, to decide which lives deserve to be lived. Preserving the integrity of time, with all its flaws and horrors, might be the most important responsibility we have. Our shared history, the unbroken chain of cause and effect, is what gives our lives context and meaning. To disrupt it would be to cast ourselves and all of humanity adrift in a sea of chaos. So we find ourselves staring at two conflicting portraits of time. One is the time of our consciousness, a flowing, personal, and emotional river, shaped by memory and anticipation. The other is the time of physics, a dimension interwoven with space, perhaps frozen in a single block, or perhaps a statistical illusion born of entropy, or maybe a cyclical loop where universes are born, die, and are born again. Was time even present at the beginning, or did it, too, emerge from the singularity of the Big Bang, meaning the question, what came before, is meaningless, like asking what is north of the North Pole. Perhaps time itself is not fundamental at all. Some physicists now believe the universe can be described by relationships alone, a network of interactions where time is not a necessary ingredient but an emergent property, something that appears only at our macroscopic scale. In this timeless reality, there is no before or after, only a web of connections. Change is not a process that happens in time, but a rearrangement of the entire cosmic structure. Ultimately, the deepest questions about time may not be about physics, but about us. Why are we, as conscious beings, so exquisitely tuned to its apparent flow? The universe may not have an arrow of time, but our minds certainly do. We are creatures of memory and hope, forever standing on the shore between what was and what will be. Perhaps the final mystery is not whether we can travel through time, but why we experience it at all. And in this moment, as you consider these ideas, you are doing what humans have always done, using consciousness to step outside the present, to reflect on the past, and to imagine the future. And that, in its own way, is the only form of time travel we have ever truly known. Our human experience of time is intensely personal, a subjective current shaped by the intricate architecture of our brains. The sensation of a minute stretching into an eternity during moments of fear or anticipation, or an hour of joy vanishing in what feels like a blink, is a direct consequence of how our neural networks process reality. The prefrontal cortex, the cerebellum, and the basal ganglia are not merely passive timekeepers, they are active storytellers, constructing our perception of duration, sequence, and flow. When we are faced with novel or dangerous situations, our brain enters a state of high alert, recording a much denser stream of sensory data. This increased information density creates the illusion that time is slowed down, allowing us to process critical details for survival. Conversely, during routine and repetitive activities, the brain operates on a kind of autopilot, conserving energy by not recording every mundane detail. This is why entire weeks of a familiar commute can blur into a single, indistinct memory, creating the sensation that time is flying by. This malleability extends to our most cherished and painful memories. What we call the past is not a static film stored in a cerebral vault, but a dynamic, living narrative that is reconstructed and subtly altered every time we access it. The very act of remembering is an act of recreation. The emotions we feel in the present can bleed into the colors of our memories, softening the edges of a past trauma or amplifying the glow of a cherished moment. This is not a defect in our cognitive machinery. It is its fundamental nature. Our memory is not a pristine, unchangeable archive, but a fluid, adaptive map, constantly being redrawn to help us navigate the complexities of the future. The reliability of this internal map is further challenged when we consider its cultural dimensions. The Western conception of time as a linear, forward-moving arrow with a distinct past, present, and future is not a universal human experience. Many Eastern philosophies, such as those found in Vedic and Buddhist traditions, perceive time as cyclical. In these worldviews, the universe undergoes immense cycles of creation and destruction, where the past is not a lost country but a recurring pattern, destined to reappear in a new form. This cyclical understanding transforms the very meaning of fate and the possibility of change. If all events are part of a repeating cosmic drama, then changing the past might simply mean making a different choice in the next turn of the Great Wheel. These profound differences in cultural perception reveal that our sense of time is not just a biological phenomenon, but a deeply ingrained cultural construct. It is a shared story we tell ourselves to make sense of the world, and different cultures tell very different stories. This variability in our internal experience of time, from the neurological to the cultural level, forces us to confront a profound philosophical question. If our perception of time is so pliable, what can we say about the nature of time itself, independent of our minds? Does a universal objective time even exist? This question has been at the heart of a debate that has raged for centuries, long before the advent of modern neuroscience. Sir Isaac Newton, in his grand mechanical vision of the universe, conceived of time as an absolute universal entity. He imagined a great cosmic clock, ticking at the same inexorable rate for everything and everyone in the universe, an invisible drumbeat to which the entire cosmos marched in perfect synchrony. Time, in this view, was a fundamental container, a pre-existing stage upon which the drama of the physical world unfolded. However, this idea was not without its challengers. The philosopher Gottfried Wilhelm Leibniz argued against this notion of an absolute container. For Leibniz, time was not a thing in itself but merely a relational concept. It was the order of events, the before and after relationship between one thing happening and another. Without events, without change, there would be no time. The debate between these two colossal intellects remained in the realm of philosophy for over 200 years, a seemingly unresolvable clash of abstract ideas. Then, at the dawn of the 20th century, a young and unassuming patent clerk in Bern, Switzerland, named Albert Einstein, took this philosophical debate and dragged it into the world of physical reality. With his theory of special relativity, published in 1905, he shattered the centuries-old belief in Newton's universal clock. Einstein demonstrated that time is not absolute, it is relative. It is a local, personal phenomenon that is inextricably linked to an observer's motion through space. The faster you travel through space, the slower time flows for you relative to a stationary observer. This is not a psychological illusion or a trick of perception. It is a fundamental physical fact of our universe. It has been experimentally verified countless times, with astonishing precision. Atomic clocks, the most accurate timekeeping devices ever created, when placed on fast-moving jets or orbiting satellites, tick measurably slower than their identical counterparts left on the surface of the Earth. This phenomenon, known as time dilation, means that an astronaut traveling at speeds close to the speed of light would age more slowly than the people they left behind. When they returned to Earth, they would have effectively jumped into the future, not by traveling through a wormhole, but by simply waiting for the future to arrive at a different rate. This revelation was just the beginning of Einstein's revolution. 10 years later, in 1915, he unveiled his general theory of relativity, which revealed an even deeper and more profound truth about the nature of time. Gravity, he showed, is not a force that acts across space, but a curvature in the very fabric of space-time itself. Massive objects, like stars and planets, do not pull on each other from a distance. They warp the four-dimensional continuum of space-time around them, and other objects simply follow these curves. And just as gravity bends space, it also bends time. The stronger the gravitational field, the slower time flows. This effect, though minuscule in our everyday lives, is real and measurable. The GPS satellites orbiting the Earth must constantly adjust their internal clocks to account for the fact that time is running slightly faster for them in their weaker gravitational field than it is for us on the ground. Without these relativistic corrections, our GPS systems would become inaccurate by several kilometers every single day. The consequences of this gravitational time dilation become extreme in the vicinity of the most massive objects in the universe, black holes. Near the event horizon of a black hole, the point of no return, the gravitational pull is so immense that time slows to a near standstill relative to a distant observer. An astronaut hovering just outside this boundary for a few hours could return to their spaceship to find that centuries, or even millennia, had passed for their crewmates. This means that two observers, living in the same universe, can experience time passing at vastly different rates. Time is not a universal river flowing at a constant speed. It is a network of local streams, each flowing at its own pace, determined by speed and gravity. Einstein's discovery provided the first truly scientific foundation for the concept of time travel. If time is a malleable dimension that can be bent and warped, why can't we bend it back on itself? Why can't we navigate this four-dimensional landscape, moving into the past as easily as we move through space? This question continues to occupy the minds of physicists and philosophers alike. The idea that time has a bendable, dynamic structure raises the tantalizing possibility that it is not a fixed, insurmountable wall, but a path we can learn to traverse. While relativity tore down the classical notion of a universal now, it still left the direction of time largely intact. The laws of physics, for the most part, seem to be time-symmetric. The equations that govern the motion of planets, the behavior of electromagnetic fields, and the interactions of subatomic particles work just as well running backward as they do forward. The physics that describes a glass falling from a table and shattering on the floor is the same physics that would describe the shards of glass spontaneously reassembling and leaping back onto the table. Yet, in our macroscopic world, we only ever witness the former. Glasses break, they do not unbreak, Eggs scramble, they do not unscramble. Time, in our experience, has a clear and unambiguous direction. This one-way street, this relentless forward march, is often referred to as the arrow of time, and its origins are one of the deepest mysteries in physics. The most widely accepted explanation for this arrow comes from the second law of thermodynamics. This fundamental law states that in any closed system, the total amount of entropy, or disorder, will always increase over time. The universe began in a state of incredibly low entropy, a highly ordered, hot, dense state at the Big Bang. Ever since then, it has been on a one-way journey toward greater disorder. A pristine sandcastle on a beach is a state of low entropy, a highly ordered structure. Over time, the wind and the waves will inevitably break it down, scattering the grains of sand into a disordered, high-entropy state. The sandcastle will never spontaneously reassemble itself from the scattered grains. This is the statistical reality that governs our universe. The forward flow of time, in this view, is not a fundamental property of the laws of physics themselves, but an emergent consequence of the universe's initial conditions. It is a statistical trend, an inevitable slide from order to chaos. Our own psychological experience of time seems to be tied to this thermodynamic arrow. We remember the past, but not the future, because the act of forming a memory is itself an entropy-increasing process. It requires energy, and the dissipation of that energy as heat increases the overall disorder of the universe. So, we are creatures whose minds are aligned with the cosmic flow of entropy. But what if this arrow is not absolute? What if it is possible, under some extreme conditions, to reverse it? If we could somehow learn to control entropy, to locally decrease disorder in a controlled way, could we reverse the flow of time itself? This remains a highly speculative idea, but it highlights the possibility that the direction of time is not an immutable law, but a conditional one. If the past is defined as the direction of lower entropy, and the future as the direction of higher entropy, then intervening in the past would mean finding a way to rewind this cosmic process, to turn back the tide of universal disorder. The dream of reversing the arrow of time, of traveling into the past, immediately collides with a formidable wall of logic, the grandfather paradox. This classic thought experiment lays bare the potential for self-contradiction inherent in any attempt to alter history. Imagine you construct a time machine and travel back 70 years to the time when your grandfather was a young, unmarried man. You find him and, for some reason, you prevent him from ever meeting your grandmother. As a result of your actions, your own parent is never conceived, and therefore, you are never born. But if you were never born, who was it that traveled back in time to commit the act in the first place? The paradox is a perfect, self-negating loop. Your success in changing the past eliminates the very possibility of you ever having existed to make the change. This seemingly insurmountable contradiction has led many to conclude that travel to the past is a logical, and therefore physical, impossibility. However, the human mind, in its relentless pursuit of solutions to even the most seemingly impossible questions, has developed several ingenious, though highly theoretical, ways to navigate this logical minefield. The most popular of these is the multiverse theory, or the many worlds interpretation of quantum mechanics. In this view, every quantum measurement, every decision point, causes the universe to split into multiple parallel realities, each representing a different possible outcome. When a time traveler goes back and alters a past event, they are not actually changing their own history. Instead, their action causes the timeline to branch, creating a new, alternative universe. In this new reality, their grandfather never meets their grandmother, and a version of them is never born. However, their original universe, the one they came from, remains completely unchanged. The time traveler is now in exile, a refugee from their own timeline, forever marooned in a parallel history that they themselves created. The paradox is resolved, but at the cost of an infinite number of parallel worlds. Another, more conservative solution to the grandfather paradox is the self-consistency principle, championed by physicists like Igor Novikov. This principle proposes that the universe itself has a built-in censorship mechanism that prevents any action that would create a logical paradox. The laws of physics, in this view, would actively conspire to ensure the consistency of the timeline. If you were to travel back in time to try and kill your grandfather, something would always prevent you from succeeding. The gun would inexplicably jam. You would slip on a banana peel at the critical moment. A sudden, out-of-the-blue distraction would cause you to miss. Or perhaps, most subtly, you would find that you simply cannot bring yourself to do it. In this model, time travel to the past is possible, but you are not an editor of history, you are a participant. Your presence and actions in the past were already a part of the causal chain of events that led to your own birth and your eventual journey back in time. You cannot change the past because your journey into it is what made the past what it was. You might discover that the mysterious stranger who saved your young grandfather from a falling piano, thus ensuring your own existence, was in fact you. This creates a self-consistent, closed loop in time, known as a bootstrap paradox, where an event or piece of information has no clear origin but simply exists as a part of the timeline's immutable structure. These theoretical solutions, while still far beyond our technological reach, demonstrate the profound and multi-layered nature of the problem. Interfering with the past is not just a technological challenge, it is a logical and ontological one. It forces us to confront the very nature of causality, reality, and our place within the grand unfolding tapestry of the cosmos. So, the strange and counterintuitive nature of the quantum realm offers yet another perspective on the nature of time, one that might dissolve the very foundations upon which our classical paradoxes are built. At the subatomic level, the neat linear progression of cause and effect begins to break down. One of the cornerstone principles of quantum mechanics is superposition, the idea that a particle can exist in multiple states or locations simultaneously. In the famous thought experiment proposed by Erwin Schrödinger, a cat in a sealed box is linked to a quantum event, such that it is considered to be both dead and alive at the same time until the box is opened and a measurement is made. At that moment, the cloud of possibilities collapses into a single definite reality. Could this principle of superposition also apply to time itself? Could an event exist in a temporal superposition, being both in the past and the future simultaneously? Until it is observed, this radical idea suggests that time is not a fixed, one-dimensional line, but a probabilistic cloud of potential moments. If this were the case, then time travel would not be about moving along a pre-existing track. It would be more akin to navigating a landscape of possibilities, choosing which temporal state to collapse into reality. Rather than changing a fixed past, a time traveler might be selecting which of many potential pasts becomes the one that is actualized. While the temporal superposition of macroscopic events has not been experimentally verified, scientists do not rule out the possibility that time itself fluctuates at the quantum level. This concept challenges our perception of a single, immutable past, suggesting instead that there may be a multitude of different pasts, all coexisting in a state of potential, and we only ever experience one of them as real. This quantum fuzziness is further amplified by the phenomenon of entanglement, an effect that Albert Einstein famously derided as spooky action at a distance. When two particles become entangled, they form a single unified quantum system, even if they are separated by vast distances. A measurement performed on one particle will instantly influence the state of the other, faster than a signal could travel between them at the speed of light. This apparent violation of the cosmic speed limit has been confirmed by numerous experiments, known as Bell tests, since the 1980s. These tests have shown that the connection between entangled particles is real and cannot be explained by any classical, hidden information. Entanglement raises profound questions about the nature of time and causality. In some experimental setups, it becomes impossible to determine which of two entangled events occurred first. This ambiguity suggests that, at the most fundamental level, time may not be a strictly one-way forward-moving process. Perhaps events are not always neatly ordered in a sequential chain, but can occur in a simultaneously connected manner. If time is bent and intertwined within the fabric of entanglement, then the past and the future are not independent points on a timeline, but interconnected parts of a holistic system that exists all at once. Time travel, in this context, might not involve traversing a physical distance through time, but rather rearranging the internal relational structure of events. It would be a journey not through a landscape, but through the very logic of the universe, the quantum world, with its inherent uncertainty and non-locality, hints at a reality where the rigid boundaries between past, present, and future are not as solid as they appear. It suggests a universe where time is not a monolithic, absolute entity, but a complex, emergent phenomenon woven from the probabilistic threads of the quantum foam. The culmination of these ideas from relativity and quantum mechanics leads us to one of the most profound and unsettling models of time ever conceived, the block universe. This theory, which finds its roots in Einstein's concept of a four-dimensional spacetime, proposes that all of time, every moment from the Big Bang to the ultimate end of the universe, exists simultaneously. The past, the present, and the future are not distinct states, but different locations in a single, static, four-dimensional block. In this model, time does not flow like a river. It is more like a frozen landscape, a map that contains all of history and all of the future laid out at once. Our conscious experience of the passage of time is merely an illusion, a product of our consciousness moving through this pre-existing block, like a spotlight illuminating one frame of a vast cosmic film at a time. The dinosaurs are not gone. Their existence is simply located in a different part of the space-time block. The future, with all its triumphs and tragedies, is not unwritten. It has already happened. Just in a different location on the map, we are simply not there yet. This idea of a static, preordained reality resurrects the age-old philosophical debate about determinism and free will. If the entire history of the universe is already written, then are our choices, our struggles, our hopes, all just an illusion? Are we simply actors playing out a script that was finalized at the dawn of time? This deterministic view reached its zenith in the 19th century with the thought experiment of Laplace's demon, a hypothetical intellect that, if it knew the precise position and momentum of every particle in the universe, could calculate the entire past and future with perfect accuracy. For Laplace's demon, the universe is a giant, deterministic clockwork machine. Quantum mechanics, with its inherent randomness and probability, seems to provide a powerful counter-argument to this rigid determinism. The behavior of particles at the subatomic level is not certain, but probabilistic. The future, from a quantum perspective, is not a single, pre-written line, but a branching tree of countless possibilities. Each quantum event, each measurement, prunes some of these branches and allows others to grow. However, even within the framework of quantum mechanics, some interpretations, like the many worlds theory, still lead to a form of determinism. Every possible outcome of a quantum event happens, just in a different parallel universe. In this view, there is no single future, but an infinite number of futures, all of which are real. The block universe model, if correct, would have staggering implications for the concept of time travel. If the past still exists as a real place within the space-time block, then traveling to it might be theoretically possible. It would not be a journey through a temporal flow, but a movement to a different coordinate in the four-dimensional map. The real question would then become a technological one. How could one navigate this cosmic map? Perhaps with the right technology, one could re-enter a past moment simply by changing their location in the space-time continuum. This would mean that the past is not gone forever, but is still there, waiting to be revisited. And if it can be revisited, perhaps it can be altered. Or perhaps, as the self-consistency principle suggests, any journey to the past would only reveal what was already a part of the block's immutable structure. The block universe model presents us with a vision of reality that is both elegant and terrifying, a universe where all of existence is a single, timeless entity, and our lives are but a brief flicker of awareness within its infinite expanse. The question of whether time had a beginning is inextricably linked to the origin of the universe itself. For millennia, the creation of the cosmos was a subject for mythology and theology, but in the 20th century, it became a question for science. The Big Bang Theory, our current best model, suggests that the universe began approximately 13.8 billion years ago from a state of unimaginable density and temperature, and has been expanding and cooling ever since. But did time itself begin with the Big Bang? If the universe emerged from a singularity, a point of infinite density where the laws of physics break down, then it is possible that time, as we know it, also came into being at that moment. In this view, asking what came before the Big Bang is a meaningless question, akin to asking what is north of the North Pole. There is no before if time itself did not exist. The physicist Stephen Hawking, along with James Hartle, proposed a no-boundary model of the universe that elegantly sidesteps this issue of a beginning. They suggested that if we were to travel back toward the Big Bang, the nature of time would change. It would lose its linear, directional quality and become more like a dimension of space. At the very moment of the Big Bang, space and time would merge into a single, four-dimensional, curved surface with no edge and no beginning. The universe would be a self-contained entity, coming into existence from nothing, without the need for a creator or a first cause. This model would make travel to a time before the universe a physical impossibility, as such a time simply does not exist. However, other theories, particularly in the realm of quantum cosmology, suggest that time may have existed before our universe. Some models propose that our universe arose from a quantum fluctuation in a larger, pre-existing vacuum, a sort of cosmic foam from which new universes are constantly bubbling into existence. In this scenario, our Big Bang was not the beginning of everything, but just the beginning of our particular pocket of reality. Time, in this view, could be a more fundamental aspect of a larger multiverse, with our universe's timeline being just one of many. If time is not a product of our universe, but an independent entity, then the past could extend infinitely beyond our cosmic horizon. Changing the past would then not only be a matter of manipulating physical events within our universe, but of understanding and potentially interacting with the very nature of this deeper, cosmic time. Understanding the origin of time is therefore fundamental to any discussion of its manipulation. It defines the very boundaries of the past we seek to explore or alter. Is the past a finite story with a clear first chapter, or is it a single volume in an infinite library of cosmic histories? The answer to this question lies at the very edge of our scientific and philosophical understanding. If our grandest theories of physics, from relativity to quantum mechanics, suggest that time may not be the fundamental, flowing river we perceive it to be, then we are forced to confront an even more radical idea: is time itself an illusion? And if time is an illusion, is the past also a part of that illusion? When we examine the fundamental laws of nature, we find that most of them are time-symmetric. They do not distinguish between the past and the future. The arrow of time, the one-way flow we experience, seems to be a product of thermodynamics, a statistical trend toward increasing disorder, not an intrinsic property of time itself. This suggests that our deeply ingrained sense of a flowing time, with a fixed past and an open future, may be a construct of our own minds. Our brains are wired to perceive events in sequence, to create a narrative of cause and effect. Our memory system stores experiences of what has happened, creating our concept of the past, while our prefrontal cortex constantly generates models and predictions of what might happen next, creating our sense of the future. But what if this mental sequencing does not exist in the external world? What if the past, present, and future are simply mental maps we use to navigate a timeless reality? This idea is not just an abstract philosophical thought, it has profound implications. If what we call the past is not an absolute, unchangeable reality, but a narrative produced by our brain, then the act of changing the past takes on a new meaning. It would not require reversing physical events in the external world, but rather transforming the mental representation of those events. Our feelings about the past are constantly changing. Traumatic events can be reframed through therapy, their emotional weight reduced. Nostalgic memories can be colored by present-day emotions. This flexibility of our mental relationship with the past suggests that even if the physical events are fixed, their effect on us is not. This is where the boundary between the physical and the psychological becomes blurred. If time is indeed an illusion, and the past is a part of that grand illusion, then what we need to change is not a fixed point in cosmic history, but the sequence of experiences recorded in our minds, the story we tell ourselves about who we are and where we came from. Such a change, while not requiring a time machine, could be just as profound, fundamentally altering our individual realities and forcing us to rethink every concept we hold dear about time, memory, and the nature of existence itself. The paradoxes that haunt the concept of time travel are not merely intellectual puzzles, they are deep probes into the logical structure of reality. The grandfather paradox, in its elegant simplicity, seems to suggest that the universe has a fundamental protection against self-contradiction. But what if the paradox is not a wall, but a doorway to a different understanding of how the universe works. The multiverse theory offers one such doorway, proposing that every act of changing the past creates a new, parallel reality. In this view, you can travel back and prevent your grandfather from meeting your grandmother, but you do not erase yourself from existence. Instead, you create a new timeline where you were never born. While your original timeline continues on, unaffected, you become a temporal refugee, an anomaly in a universe that is not your own. The paradox is resolved, but at the price of an infinite number of branching realities. An alternative solution, the self-consistency principle, proposes a universe that is inherently paradox-proof. It suggests that any attempt to change the past is doomed to fail, not because of some mystical force, but because the laws of physics themselves would ensure that the timeline remains consistent. Your journey to the past, and every action you take, were already part of the historical record that led to your existence. You cannot change history, because you are a part of it. This idea leads to the equally mind-bending concept of the bootstrap paradox, where an object or a piece of information can exist in a closed causal loop, with no discernible origin. Imagine a time traveler who is a great admirer of Shakespeare. They travel back to Elizabethan England with a complete collection of Shakespeare's plays, only to find that Shakespeare himself does not exist. In a panic, to ensure the plays are still written, they publish the works under Shakespeare's name. The question then becomes who actually wrote the plays. The information exists in a loop, with no starting point. These theoretical solutions, the multiverse and self-consistency, do not necessarily rule out the possibility of time travel. Instead, they place profound limits on what it might entail. They suggest that time is not a fragile, easily broken thread, but a robust system that either contains its own solutions to paradoxes or prevents them from forming in the first place. Solving these logical conundrums may be the key to unlocking a deeper understanding of the nature of time. Perhaps the universe is not as fragile as we think. Perhaps it is a system that is far more complex, more resilient, and more mysterious than our linear cause and effect minds can easily comprehend. The ultimate boundary for any journey through time and space appears to be the speed of light. According to Einstein's theory of relativity, nothing with mass can ever reach, let alone exceed, this cosmic speed limit. As an object accelerates, its mass increases, and the energy required to accelerate it further grows exponentially. At the speed of light, its mass would become infinite, requiring an infinite amount of energy to move it. This makes faster-than-light travel a physical impossibility within our current understanding of physics. However, let us, for a moment, indulge in a thought experiment. Let us assume that a way is found to circumvent this universal speed limit. What would be the consequences for the flow of time? Scientists believe that exceeding the speed of light would be tantamount to reversing the direction of time. This is because it would fundamentally violate the principle of causality, the idea that a cause must always precede its effect. If a particle could travel faster than light, it would be possible for some observers to see the effect of an event before they see the cause. An arrow could be seen hitting a target before it was fired from the bow. This would mean that the past could be influenced from the future, that the sequence of events could be rewritten. The logical and physical obstacles to this are immense. Physicists have hypothesized the existence of particles called tachyons, which are born moving faster than light and can never slow down to sublight speeds. However, the existence of tachyons has never been experimentally confirmed, and they remain in the realm of theoretical speculation. The existence of such a particle could potentially allow for communication with the past, creating a kind of temporal telephone line, but it would also open a Pandora's box of paradoxes. Nevertheless, the idea that the speed of light acts as a kind of time barrier is a powerful one. It suggests that time is not a fixed, forward-moving line, but is intrinsically linked to the fundamental constants of the universe. If the speed of light is a wall that separates us from faster-than-light travel, it may also be the wall that separates the present from the past. Overcoming this barrier would not just be a feat of engineering, it would mean overcoming the very structure of time itself. While this remains a theoretical playground for physicists and science fiction writers, it lies at the very heart of the discussion about the physical conditions required to intervene in the past and reshape the flow of cosmic history. Ultimately, the question of time travel, of changing the past or shaping the future, may be a uniquely human obsession, born from our own consciousness and our relationship with memory and regret? What if the universe itself has no such preoccupations? What if the flow of time, the very thing we seek to control, is nothing more than an emergent property of our own limited perception? When we look at the fundamental equations that describe the universe, from Newton's laws of motion to Schrödinger's quantum equation, we find that they are, for the most part, time-symmetric. They run just as well backward as they do forward. The laws of nature, at their deepest level, do not seem to care about the direction of time. The only major physical law that seems to impose a direction is the second law of thermodynamics, which states that entropy, or disorder, always increases. The universe moves from a state of low entropy at the Big Bang to a state of ever-increasing disorder. This thermodynamic arrow of time seems to dictate the one-way flow we experience in our macroscopic world. But this is a statistical law, a trend, not a fundamental, inviolable rule for time itself. This suggests that the flow of time may be an illusion, a story our brains tell us to make sense of a reality that may be timeless. Our memory records the past, and our expectations plan for the future. But this sequencing of events may not exist in the external world. It may be a purely mental construct. If time does not truly flow, then the past and the future are not distant lands, but mental maps. In this case, changing the past would not mean altering a physical event that has already occurred, but reorganizing the record of that event in our minds. The directionless nature of physical laws at the fundamental level strengthens the possibility that the past is not a fixed, immutable reality, but a flexible, rewritable narrative. And if that is the case, then we are all, in a sense, time travelers, constantly reshaping our own past through the very act of remembering them. The most profound journey may not be to a distant point in history, but to a deeper understanding of the here and now, and the role our own consciousness plays in creating the river of time in which we feel we are flowing.
Imagine a cat, sealed inside a box, its fate tied to the whims of a single radioactive atom. If the atom decays, an event governed entirely by the probabilistic laws of quantum mechanics, a vial of poison is shattered, and the cat dies. If the atom does not decay, the cat lives. According to our classical everyday intuition, the cat inside the box is definitively either one or the other. We simply do not know which until we open the box and look. But this is not what quantum mechanics tells us. It tells us something far stranger, something that strikes at the very heart of our understanding of reality. It tells us that until the moment of observation, the atom exists in a superposition of states it has both decayed and not decayed simultaneously. And because the cat's fate is inextricably linked to the atoms, the cat, too, must exist in a superposition. It is, in the bizarre language of quantum physics, both alive and dead at the same time, a ghostly blend of two mutually exclusive realities coexisting in a single, unobserved space. This is Erwin Schrödinger's famous thought experiment, and it was not designed to be a literal description of feline biology, but rather a dramatic, macroscopic metaphor to expose the profound absurdity and the deep philosophical paradox that arises when the strange rules of the quantum world are scaled up to the world of our everyday experience. We never see a cat that is both alive and dead. The moment we open the box, the moment we make a measurement, this cloud of possibilities, this wave function, collapses into a single, definite reality. The cat is either alive or it is dead. The act of observation seems to be the trigger that forces the universe to make a choice. But how? And why? This is the quantum measurement problem, one of the deepest and most unresolved mysteries in all of science. It forces us to ask a question that feels more philosophical than physical. Does reality exist independently of our observation of it? Or is the universe a participatory one, a reality that only solidifies, only becomes real when a conscious observer, or at least a measuring device, interacts with it? This idea is not just a scientific curiosity, it is a profound challenge to our sense of an objective, external world. It suggests that the boundary between the observer and the observed is not as clear as we once thought, that we are not passive spectators watching a pre-existing cosmic drama, but active participants co-creating the script as we go along. Schrödinger's cat, in its sealed box, becomes a symbol for every unobserved potential, every undecided future, every unexamined corner of our own consciousness. It is a metaphor for the state of our own minds as we drift into sleep, a state where the rigid certainties of the waking world dissolve, where logic and contradiction can coexist, where we are both here and not here, both ourselves and someone else entirely. In the comforting darkness of this quantum uncertainty, we surrender the act of measurement and allow ourselves to float in the pure, uncollapsed sea of possibility, a sea from which all realities, both in the cosmos and in our own minds, are born. The strange state of Schrödinger's cat is built upon the foundational principle of quantum superposition, a concept that is as fundamental to the quantum world as gravity is to the classical one. Superposition dictates that a quantum system, like an electron or a photon, can exist in a combination of multiple, seemingly contradictory states at the same time. As long as it is not being measured, an electron does not have a single, definite position. It exists as a probability wave, a cloud of potential locations spread out over a region of space. It is not here or there. It is, in a sense, both here and there. A photon can be polarized both vertically and horizontally simultaneously. An atom can be in both a high-energy and a low-energy state at once. This is not a matter of our ignorance. It is not that we simply do not know the particle's true state. The particle's true state is this combination of all possible states. The most famous and elegant demonstration of this is the double-slit experiment. If you fire a single electron at a barrier with two slits in it, and you do not watch to see which slit it goes through, the electron behaves not like a particle, but like a wave. It seems to pass through both slits at the same time, creating an interference pattern on the detector screen behind the barrier, a series of bright and dark bands that is the classic signature of two waves interfering with each other. It is as if the electron's own probability wave splits, passes through both slits, and then interferes with itself. This happens even if you fire only one electron at a time. The single electron, somehow, knows about the existence of both paths and behaves accordingly. However, the moment you place a detector at one of the slits to see which path the electron takes, the magic disappears. The interference pattern vanishes. The electron behaves like a well-behaved particle, passing through one slit or the other, but not both. The very act of measurement, of gaining information about the electron's path, forces it to abandon its wave-like superpositional nature and choose a single, definite reality. This is not just an abstract concept, it is the engine behind the next technological revolution. The power of quantum computers lies in their ability to harness superposition. A classical computer bit can be either a 0 or a 1, but a quantum bit, or qubit, can be a 0, a 1, or a superposition of both at the same time. This allows a quantum computer to perform a vast number of calculations simultaneously, giving it the potential to solve problems that are intractable for even the most powerful classical supercomputers. But perhaps the most fascinating aspect of superposition is its echo in our own subjective experience. As we lie on the edge of sleep, in the hypnagogic state, our minds enter a similar realm of fluid possibility. The rigid categories of waking thought dissolve. We are not fully awake, nor fully asleep. Memories, thoughts, and images from different times and places can coexist and merge in strange and beautiful ways. We can feel both the comfort of our bed and the sensation of floating in a distant, imagined landscape. This is a mental superposition, a state where the mind is no longer collapsed into a single, definite stream of consciousness, but exists as a shimmering cloud of potential experiences. It is in this state that the seeds of our dreams are sown, a state where the strict logic of the classical world gives way to the poetic, associative logic of the quantum realm. Superposition is not just a mathematical tool for physicists, it is an invitation to see the world, and ourselves, not as a collection of fixed, solid objects, but as a dynamic, vibrant, and endlessly creative sea of possibilities. The transition from the probabilistic, superpositional world of quantum mechanics to the definite, classical world of our everyday experience is known as the collapse of the wave function, and it lies at the heart of the quantum measurement problem. The wave function is the mathematical object that describes the probability cloud of a quantum system. It contains all the information about all the possible states the system can be in. As long as the system is isolated, the wave function evolves smoothly and predictably according to the Schrödinger equation, a continuous, wave-like evolution. But the moment a measurement is made, something dramatic and discontinuous happens. The wave function instantaneously collapses, and only one of the many possibilities becomes the single, actual reality. This collapse is not described by the Schrödinger equation. It is a separate, ad hoc rule that we have to add to the theory to make it match our observations. But what constitutes a measurement? What is the magical ingredient that causes this collapse? This is the question that has divided physicists for a century. The Copenhagen interpretation, the historical orthodoxy developed by Niels Bohr and Werner Heisenberg, takes a pragmatic and somewhat mysterious view. It posits a fundamental split between the quantum world and the classical world of our measuring devices. When a quantum system interacts with a classical measuring device, the collapse just happens. The interpretation does not explain how or why it happens, it simply states that it does, and that our job as physicists is to calculate the probabilities of the different outcomes. This is a deeply unsatisfying answer for many, as it leaves the boundary between quantum and classical ill-defined and elevates measurement to a special, almost mystical, status. In response to this dissatisfaction, other interpretations have been proposed. The many worlds interpretation, first proposed by Hugh Everett III, offers a radical and elegant solution. There is no collapse. The wave function never collapses. When a measurement is made, all possible outcomes actually happen. The universe itself splits or branches into multiple parallel universes, one for each possible outcome. In one universe, the atom in Schrödinger's box decays and the cat is dead. In another, it does not, and the cat is alive. The observer also splits, with one version of you seeing the dead cat and another version seeing the living one. In this view, measurement is not an act that collapses reality, it is an act that entangles the observer with the system, splitting the world into different, non-communicating branches. There is no special measurement process. There is only the smooth, continuous evolution of the universal wave function. Another class of theories, known as objective collapse or spontaneous collapse models, proposes that the collapse is a real physical process. It is not caused by an observer, but happens spontaneously and randomly. For a single particle, this spontaneous collapse is incredibly rare. But for a macroscopic object, which consists of a vast number of particles, the probability of one of them collapsing becomes incredibly high, leading to an almost instantaneous collapse of the entire object's wave function. This is why we never see macroscopic objects like cats in a superposition. They are simply too large and complex to maintain their quantum coherence for any significant amount of time. The measurement problem remains one of the most profound and open questions in all of science. It is a question that probes the very nature of reality, the role of the observer, and the boundary between the potential and the actual. And it is a question that resonates with the experience of falling asleep. As we close our eyes and turn our attention inward, the constant stream of measurements from the external world ceases. The neural windows of perception close, and our consciousness is no longer being constantly collapsed by the influx of sensory data. It is in this state of sensory deprivation that the mind is free to explore its own internal quantum universe, a universe of uncollapsed possibilities, of fluid associations, of dream-like superposition. The act of sleeping is, in a sense, a voluntary suspension of the measurement process, an act of surrendering to the pure, uncollapsed potential of our own consciousness. The inherent fuzziness of the quantum world, the fact that a particle can be in many places at once, is inextricably linked to another fundamental principle, Heisenberg's uncertainty principle. This principle is not a statement about the limitations of our measuring devices. It is a fundamental, built-in property of the universe itself. It states that there are certain pairs of physical properties, known as conjugate variables, that cannot both be known with perfect precision at the same time. The most famous of these pairs is position and momentum. The more precisely you measure the position of a particle, the less precisely you can know its momentum, and vice versa. There is an irreducible trade-off, a fundamental limit to our knowledge. Imagine trying to measure the position of an electron To see it, you have to bounce something off of it, like a photon of light. To get a precise measurement of its position, you need to use a photon with a very short wavelength, which means it has a very high energy. But when this high-energy photon hits the electron, it gives it a powerful kick, changing its momentum in an unpredictable way. The very act of measuring the position has made the momentum uncertain. Conversely, if you want to measure the momentum precisely, you need to use a low-energy photon, but this has a long wavelength, which gives you a very fuzzy, imprecise measurement of its position. It is a cosmic game of catch-22, a game we can never win. This principle is not just a theoretical curiosity, it has profound and tangible consequences. It is the reason that atoms are stable. If an electron could have a precise position and zero momentum, it would just sit at the bottom of the atom's potential well, right on top of the nucleus. But the uncertainty principle forbids this. If its position were perfectly known, its momentum would be infinitely uncertain, meaning it could have a huge velocity, and it would not stay there. Instead, the electron exists in a probability cloud around the nucleus, a compromise between being close to the nucleus and having a spread-out position. The uncertainty principle is also the source of the zero-point energy of the vacuum, the ever-present quantum jiggle that prevents anything from ever being truly still. And it has a deep and beautiful echo in our own mental and emotional lives. We can focus intently on one aspect of our experience, a single thought, a specific feeling, a detailed plan for the future. But the more we focus on that single point, the more the vast landscape of other possibilities, other feelings, other potential futures becomes uncertain and fuzzy. We can know the what of our present moment with great clarity, but in doing so, we lose sight of the where to of our potential paths. As we prepare for sleep, this mental uncertainty becomes a palpable experience. We try to hold on to a single thought, to solve a problem, to plan the next day. But the more we try to pin it down, the more other thoughts and feelings intrude, pulling us into a state of fluid, associative thinking. The conscious, controlling mind begins to lose its grip, and we are drawn into the gentle, welcoming embrace of uncertainty. This is not a failure of control, it is a necessary surrender. It is in this state of mental uncertainty that the creative, restorative processes of sleep can begin. The mind is no longer confined to a single track, but is free to explore the vast, interconnected web of memories, emotions, and possibilities that make up our inner world. The uncertainty principle, at both the quantum and the psychological level, is not a limitation on our knowledge, but an opening to a deeper, richer, and more creative form of existence. It is the universe's way of telling us that not everything can or should be known with perfect certainty, and that in the spaces between our knowledge, in the gentle fog of the unknown, lies the true source of all creativity and all change. Perhaps the most spooky and counterintuitive of all quantum phenomena is entanglement. It is a strange and intimate connection that can exist between two or more particles, a bond so deep that it seems to transcend the normal rules of space and time. When two particles, like a pair of photons, are created in a certain way, their quantum states can become entangled. This means that they are no longer independent entities, but are part of a single, unified quantum system, described by a single wave function. The strange part is that this connection persists no matter how far apart the particles are separated. If you take these two entangled photons and send them to opposite ends of the galaxy, they will remain linked. The real spookiness comes in when you make a measurement. According to quantum mechanics, a property of a particle, like its polarization, is not determined until it is measured. It exists in a superposition of all possible polarizations. But with an entangled pair, the moment you measure the polarization of one photon and find it to be, say, vertical, you instantly know that its distant partner, light years away, will be found to be horizontal if you were to measure it. It is as if the first photon's measurement result is instantaneously communicated to the second, in a way that seems to violate Einstein's cosmic speed limit, the speed of light. Albert Einstein famously disliked this aspect of quantum mechanics, derisively calling it spookhafte Fernwirkung, or spooky action at a distance. He believed that this apparent faster-than-light communication was a sign that the theory was incomplete, that there must be some hidden local variables that the particles carried with them, predetermining the results of the measurements. For decades, this was a philosophical debate. But in the 1960s, the physicist John Bell devised a clever mathematical theorem, now known as Bell's theorem, which showed that it was possible to experimentally distinguish between the predictions of quantum mechanics and any theory based on local hidden variables. In the decades since, numerous Bell test experiments have been performed with increasing precision, and every single one of them has confirmed the predictions of quantum mechanics and ruled out local hidden variable theories. The spooky action is real. The universe is, in some fundamental way, non-local. This does not mean that we can use entanglement to send faster-than-light signals. A measurement on one particle is random. You cannot control whether you get vertical or horizontal. You only know that your friend at the other end of the galaxy will get the opposite result. It is only when you later compare your results, a process that is still limited by the speed of light, that you can see the correlation. But the underlying connection is still instantaneous and profound. It suggests that at a deep level, the universe is not a collection of separate, isolated objects, but a single, holistic, and interconnected whole. This has deep philosophical and even spiritual resonances. Could the feeling of connection we sometimes have with a loved one far away, the sense of empathy that can span continents, the feeling of being part of a collective consciousness, be a macroscopic echo of this fundamental quantum entanglement? As we fall asleep, our sense of a separate, bounded self begins to dissolve. The rigid walls of our individual consciousness become more porous. In the dream state, physical distance often loses its meaning. We can be with people who are long gone or far away. We can feel their presence, hear their voice, experience their emotions. Perhaps in this state, our minds are more attuned to the subtle, the non-local connections that bind us to the people in the world around us. Perhaps sleep is a time when the brain's classical processing gives way, and we become more sensitive to the spooky action of our own entangled emotional and relational fields. Entanglement tells us that separation is, in some sense, an illusion. It is a powerful reminder that we are all part of a single, vast, and mysterious quantum system. A system where the connections are deeper and more profound than our classical intuition can ever fully grasp. And in the quiet intimacy of sleep, we may get our closest glimpse of this fundamental cosmic unity. The thought experiment of Schrödinger's cat serves as a powerful and enduring metaphor for the bizarre and counterintuitive nature of the quantum world. By taking the concept of superposition out of the abstract realm of subatomic particles and applying it to a familiar, macroscopic object, Schrödinger forces us to confront the profound weirdness of quantum reality head-on. The cat in the box, suspended in a ghostly state between life and death, becomes a symbol for the fundamental uncertainty and probabilistic nature that lies at the heart of existence. It is a story that highlights the central role of the observer in shaping reality. The cat's fate is not decided until we look. This raises deep questions about the nature of objectivity. Is there a world out there that exists independently of our perception of it? Or is the universe a participatory one, where the act of conscious observation is what brings reality into being? This is not just a scientific puzzle, it is an existential one. It challenges our sense of being passive spectators in a predetermined universe and suggests that we are, in a very real sense, co-creators of our own reality. This idea finds a powerful echo in our own psychological lives. We all have Schrödinger's cats in our own minds, unexamined fears, unresolved conflicts, unspoken desires, potential futures that we hold in a state of superposition. As long as we keep the box of our consciousness closed, as long as we avoid confronting these issues, they exist in a state of limbo. A difficult conversation we need to have is both had and not had. A life-changing decision is both made and not made. These uncollapsed potentials can create a constant, low-level anxiety, a sense of being stuck. The act of opening the box, of facing the fear, of making the decision, of speaking the truth is what collapses the wave function of our own lives. It can be a painful and difficult process, as we may not like what we find inside, but it is also a necessary one, as it is the only way to move from a state of uncertain potential to a state of definite reality. In this sense, the process of psychological growth and self-awareness is a process of consciously and courageously opening the boxes we have kept sealed within ourselves. Sleep and dreams provide a unique and often powerful arena for this process. In the safety of the dream state, where the stakes are not real, we can often confront our inner Schrodinger's cats in a symbolic form. We can face the monsters that represent our fears. We can explore the alternative paths that represent our unmade decisions. We can live out the consequences of our suppressed desires. Dreams are a kind of nightly, unconscious therapy, a process where the mind rehearses the act of opening the box, of collapsing the wave functions of our own psyche. The state of falling asleep itself is like entering the box. We leave the world of definite, classical reality and enter a liminal space of possibility. The last thoughts before sleep are often a superposition of the day's events and the next day's anxieties, a jumble of memories and anticipations. We are suspended, like the cat, between the past and the future, between what is and what could be. And in the dream state, we are free to explore all of these possibilities. We can see the cat both alive and dead. We can live out both the best case and the worst case scenarios. This is why sleep is not just a passive state of rest, but an active, creative, and transformative process. It is a nightly journey into the quantum heart of our own being, a journey where we confront our uncertainties, explore our potentials, and ultimately prepare ourselves to open the boxes of our own lives when we wake. The ability of a quantum particle to tunnel through a barrier that it classically should not be able to overcome is another of nature's deep and beautiful mysteries. In the classical world, if you throw a ball at a wall, it will either have enough energy to go over the wall, or it will bounce back. It will never be found on the other side of the wall if it didn't have enough energy to clear it. But in the quantum world, things are different. A particle, like an electron, is not a solid point, but a wave of probability. And this wave does not stop abruptly at a barrier. It decays exponentially into it. If the barrier is thin enough, there is a small but non-zero probability that the wave will have some amplitude on the other side. This means there is a finite chance that the particle, when measured, will be found on the far side of the barrier, having seemingly tunneled through an impossible obstacle. This is not just a theoretical curiosity, it is a phenomenon that is essential to the functioning of our universe. The sun shines because of quantum tunneling. In the core of the sun, the temperatures are not quite high enough for hydrogen nuclei to overcome their mutual electrostatic repulsion and fuse together in the way that classical physics would require. It is only because of quantum tunneling that they can get close enough for the strong nuclear force to take over and initiate the process of nuclear fusion, releasing the energy that powers our solar system. Quantum tunneling is also at the heart of many of our modern technologies. In a scanning tunneling microscope, a sharp metal tip is brought incredibly close to a surface, and the tiny quantum tunneling current that flows between the tip and the surface is used to create an image of the individual atoms on that surface. The flash memory in our computers and smartphones works by trapping and releasing electrons in a floating gate through a thin insulating barrier, a process that is only possible because of quantum tunneling. But beyond its role in physics and technology, quantum tunneling is a powerful metaphor for the human experience of overcoming obstacles. We all face barriers in our lives: fears, self-doubts, limiting beliefs, societal pressures, past traumas. These can seem like solid, impenetrable walls, and classical, logical thinking can often lead us to believe that they are insurmountable, but the human spirit, like a quantum particle, has a wave-like nature. Our consciousness, our creativity, our resilience are not confined to a single point. We have the capacity to find unexpected paths, to tunnel through the obstacles that seem to block our way. This often happens not through brute force, but through a shift in perspective, a moment of insight, a creative leap of faith. And sleep and dreams are often the crucible where this mental tunneling takes place. In the dream state, the rigid, logical barriers of the waking mind are softened. We are free to explore unconventional solutions, to make associative leaps that our rational mind would dismiss. A problem that seemed intractable during the day can suddenly find a resolution in a dream, not through a step-by-step logical process, but through a sudden, intuitive tunneling to a new perspective. We can wake up in the morning with a strange sense of clarity, a feeling of lightness, a new way forward that was not apparent the night before. This is the power of the unconscious mind to find its way through the walls of our own making. Quantum tunneling is the universe's way of telling us that no barrier is absolute. It is a message of hope, a whisper from the subatomic world that even when the way seems blocked, there is always a possibility, however small, of a breakthrough. It is an invitation to trust in the wave-like, creative, and unpredictable nature of our own being, and to remember that sometimes the only way through is through. The principle of superposition, the idea that a quantum system can exist in multiple states at once, is not just a statement about the properties of individual particles. It is a profound statement about the nature of reality itself. It tells us that the universe, at its most fundamental level, is not a collection of definite fixed things, but a dynamic, vibrant, and multi-layered web of possibilities. Reality is not a single, monolithic entity, but a superposition of all possible realities. This is a concept that is deeply challenging to our classical intuition, which is built on the either-or logic of our macroscopic world. A door is either open or closed, a person is either here or there, but the quantum world operates on a both-and logic. An electron is both a wave and a particle. A cat is both alive and dead. This multiplicity of existence is not something we can directly perceive, because the act of perception itself, the act of measurement, forces a choice. The wave function collapses, and one of the many possibilities becomes the single, experienced reality. But the underlying, unobserved reality remains a rich and complex superposition. This has a powerful and beautiful resonance with our own inner lives. The human mind is not a single, unified consciousness. We are a superposition of multiple selves, multiple desires, multiple beliefs, multiple potential life paths. We contain multitudes, the you who goes to work in the morning, the you who laughs with friends, the you who feels a deep sense of sorrow in a quiet moment. These are all different states, different aspects of a single, complex wave function of the self. We often experience this as internal conflict or indecision. We want both to pursue a safe, stable career and to follow a risky, artistic passion. We feel both love and resentment towards the same person. These are not signs of a flawed or broken psyche. They're the natural expression of our own inner quantum superposition. And nowhere is this multiplicity more apparent than in the dream state. Sleep is the nightly dissolution of the collapsed self of our waking life. The ego, the sense of a single, continuous identity, loosens its grip, and the vast superpositional nature of our consciousness is allowed to come to the fore. In dreams, we can be anyone, anywhere, anytime. We can be a child again, feeling the pure, unadulterated joy of a long-lost summer afternoon. We can be a king, a pauper, a bird, a fish. We can experience the world from a completely different perspective, inhabit a different body, live a different life. These are not just random, meaningless images. They are the exploration of our own, uncollapsed potential. They are the whispers of our other possible selves. Dreams are the theater of superposition, a stage where all the different versions of who we are, who we have been, and who we could be are allowed to play out their parts. This is why dreams can be so liberating and also so unsettling. They show us that our waking identity is just one of many possibilities, one collapsed state among an infinity of others. Superposition, at both the quantum and the psychological level, is a reminder that reality is far richer, more complex, and more mysterious than our everyday. Classical mind can comprehend. It is an invitation to embrace our own multiplicity, to honor the different and sometimes contradictory parts of ourselves, and to remember that even when we have made a choice and collapsed our reality into a single path, the echoes of all the other paths, all the other possibilities are still there, vibrating silently in the deep, superpositional sea of our own being. The phenomenon of radioactive decay provides a fascinating window into the quantum nature of time. A radioactive atom, like the one in Schrödinger's thought experiment, is an unstable system. Its nucleus has an excess of energy, and it will eventually decay, transforming into a more stable nucleus and emitting a particle. But the when of this decay is fundamentally unpredictable. We cannot, even in principle, know the exact moment that a particular atom will decay. All we can know is its half-life, the time it takes for half of a large sample of these atoms to decay. For a single atom, the moment of decay is a purely probabilistic event. It could happen in the next second, or it could happen in 1,000 years. Time, at this fundamental level, does not seem to be a smooth, deterministic flow, but a series of probabilistic quantum jumps. This state of waiting, of existing in an unstable state with a potential for transformation, is a profound metaphor for the nature of time itself. It suggests that time is not a river that carries us along at a constant speed, but a landscape of potential, where events are not predetermined, but are realized through the resolution of quantum uncertainty. The moment of decay is the moment when a possibility becomes an actuality, the moment when the wave function of the atom collapses from a superposition of undecayed and decayed into a single, definite state. Before that moment, the future is open. After that moment, the past is fixed. The decay event is a now, a point where the fog of quantum probability crystallizes into the hard fact of classical reality. This resonates deeply with our own subjective experience of time, especially in the state of falling asleep. As we drift into slumber, our rigid clock-time perception of the world begins to dissolve. The linear progression of thoughts gives way to a more fluid, associative state. Time becomes fragmented, non-linear. A 5-minute doze can feel like an hour. A long night of deep sleep can feel like it passed in an instant. In dreams, the arrow of time can be completely abandoned. We can relive moments from our distant past or experience vivid, detailed scenarios of a potential future. The mind, in this state, is operating on quantum time, a time that is not measured by the ticking of a clock, but by the unfolding of meaningful, emotional events. The decay of an atom is a physical transformation, but we also experience a form of mental decay in our own lives. A long-held belief can suddenly crumble in the face of a new experience. A deeply ingrained emotional pattern, a half-life of sorrow or anger, can suddenly transform, releasing us into a new, more stable state of being. These moments of insight and transformation are often not the result of a slow, linear process, but of a sudden, unpredictable quantum leap in our consciousness. And very often, the seeds of these transformations are sown in the quiet, timeless realm of sleep. Sleep is a state where we let go of our attachment to the linear, forward-moving narrative of our lives. We allow our consciousness to decay, to dissolve its rigid structures, and to be reborn in the morning. Time does not age us. It is our passage through the landscape of possibility, our constant process of collapsing the wave function of our own lives. That shapes who we are. The universe, at its core, is a story of transformation and decay. In all its forms, is the engine of that story. The wave-particle duality is perhaps the most central and profound paradox of the quantum world. It is the seemingly impossible fact that the fundamental constituents of our universe entities, like electrons and photons, behave sometimes like localized, solid particles, and other times like spread-out, ethereal waves. This is not a matter of them being one or the other, and we are just unsure which they are. In a deep and fundamental sense, both. Their nature is not a fixed property, but is dependent on the context of the experiment, on the question we ask of them. If we design an experiment to measure their position, to see which slit they go through, they behave like particles. If we design an experiment to observe their interference pattern, to see how they spread and interact, they behave like waves. The universe, it seems, responds to our inquiry. Our choice of measurement determines the reality we perceive. This is a radical departure from the classical, Newtonian worldview, where reality is a fixed, objective thing that exists independently of our observation. The quantum world suggests a more participatory reality, a reality that is co-created in the act of interaction. This duality is not just a feature of the subatomic world, it is a powerful metaphor for our own existence. We, too, live in a state of wave-particle duality. In our waking, everyday lives, we are particles. We have a specific location in space and time. We have a defined identity, a name, a body, a set of roles and responsibilities. We interact with the world as separate, discrete entities. But in other states of consciousness, in deep meditation, in moments of creative flow, in the throes of love, and most universally, In sleep, we experience our wave nature. Our sense of a separate, bounded self dissolves, and we feel a sense of connection to something larger. Our consciousness is no longer a localized point, but a spread-out field of awareness. Sleep is the nightly immersion into our wave-like being. As we drift off, the particle-like identity of our ego, with its sharp boundaries and constant self-monitoring, begins to fade. The borders of the self become porous. We are no longer just me, a single, isolated point of consciousness. We become a flow, a stream of images, feelings, and memories that are not bound by the normal rules of time, space, and identity. In dreams, we are the ultimate wave. We can be in multiple places at once. We can merge with other characters. We can experience a reality that is fluid, symbolic, and associative. The rigid logic of the particle gives way to the poetic, interconnected logic of the wave. This nightly oscillation between our particle self and our wave self is not just a biological necessity, it is an essential part of our psychological and spiritual health. It is a process of rebalancing, of remembering that we are not just our egos, not just the sum of our worldly achievements and failures. We are also something more, something vast, interconnected, and mysterious. We are both the finite particle and the infinite wave. The wave-particle duality is the universe's way of telling us that reality is not a simple, one-dimensional thing. It is a rich, paradoxical, and beautiful mystery. And in the rhythm of our own lives, in the daily cycle of waking and sleeping, of being and flowing, we are living out this fundamental cosmic truth. We are particles of consciousness, dreaming that we are waves. The law of radioactive decay, with its inherent unpredictability, does more than just challenge our classical notions of time. It provides a profound insight into the very nature of its arrow. We experience time as a relentless, unidirectional flow, a river that carries us inexorably from the past to the future. The second law of thermodynamics, the law of entropy, provides a physical basis for this arrow. The universe as a whole tends to move from a state of order to a state of disorder. But the quantum world suggests a more subtle and nuanced picture. The decay of a single atom is not a process that happens in time. It is an event that creates a moment of time. Before the decay, the system exists in a timeless, probabilistic state of potential. The decay itself is the collapse of this potential into a definite, historical fact. It is the crystallization of now. This perspective suggests that the flow of time is not a smooth, continuous property of the universe, but is rather a staccato sequence of such irreversible, information-creating events. The universe builds its past, moment by moment, through the resolution of quantum uncertainty. This resonates with our own experience of consciousness. Our sense of a continuous flowing present is an illusion created by our minds. In reality, our consciousness is a series of discrete moments of awareness, strung together so quickly that they create the impression of a smooth flow. Sleep is a state where this illusion is temporarily suspended. The mind is no longer engaged in the constant process of creating nows from the sensory input of the external world. It is free to roam in the timeless, probabilistic realm of the unconscious. This is why our perception of time becomes so distorted in sleep. The mind is no longer bound by the relentless, forward-moving sequence of decay-like events that constitutes our waking reality. It is in a state of pure potential, a state more akin to the undecayed atom. But this is not a passive state. In this timeless realm, the mind is engaged in a different kind of work, a work of integration, of healing, of reorganization. The decay events of our waking life, the stressful encounters, the emotional shocks, the difficult decisions leave a residue in our psyche. Sleep is the process by which our minds metabolize these events, integrating them into the larger narrative of our lives. It is a form of mental decay, a process of letting go of the old and preparing for the new. The anxieties of the day can dissolve in the quiet of the night. A difficult memory can be transformed, its emotional charge neutralized. We wake up in the morning, not as the same person who went to sleep, but as a decayed product, a new version of ourselves that has been subtly but profoundly reshaped by the timeless work of the night. The arrow of time, then, is not just a physical law, it is a psychological and spiritual one. It is the story of our own, constant transformation, our own continuous process of decaying and being reborn, a process that finds its most profound expression in the silent, mysterious, and deeply restorative alchemy of sleep. The quantum principle of superposition reveals a truth that extends far beyond the realm of subatomic particles. Reality is fundamentally multi-layered, and existence is a constant negotiation between possibility and actuality. This is not just a feature of the physical world, it is a deep and resonant truth about the nature of our own souls. We are not single, monolithic entities. We are a superposition of all our potential selves. The person you are today is just one collapsed state, one realized possibility from an infinite spectrum of potential yous. Every choice you have made, every path you have taken, has collapsed your wave function into a particular reality. But the other possibilities, the other paths, do not simply vanish. They continue to exist as a kind of quantum potential, a ghostly echo in the superpositional field of your own being. This is a concept that can be difficult to grasp intellectually, but it is one that we all experience intuitively, especially in the liminal spaces of our lives, in moments of deep reflection, in daydreams, and most powerfully, in our sleep. Sleep is the great decomposer of the singular self. The ego, with its need for a coherent, consistent narrative, relaxes its grip, and the multiplicity of the soul is allowed to emerge. In our dreams, we are not bound by the choices we have made in our waking lives. We can explore the roads not taken. We can be the artist we chose not to become, the lover we let go, the person we might have been if we had been born in a different time or a different place. These dream experiences are not just idle fantasies. They are the soul's way of exploring its own, vast superpositional landscape. They are a form of quantum exploration, a way of touching and integrating the other, potential versions of ourselves that coexist within our psyche. This is why dreams can be so emotionally powerful. They can bring a sense of profound longing for a life not lived, or a deep sense of gratitude for the life we have. They can show us aspects of ourselves, our courage, our creativity, our darkness that we have suppressed or disowned in our waking lives. They are a form of soul retrieval, a process of gathering the scattered fragments of our own potential and weaving them into a richer, the more complete sense of self. The idea that we are a superposition of souls also provides a new and beautiful way to think about our relationships with others. When we connect deeply with another person, we are not just two separate particles interacting. We are two complex wave functions, two superpositional fields, overlapping and entangling. We become part of each other's potential. The love, the wisdom, the pain we share become part of the superposition of each other's souls. This is why the loss of a loved one can feel like the loss of a part of ourselves, a part of our own superposition. A set of possibilities that was realized through our connection with them has collapsed and is no longer accessible, but the entanglement remains. The connection, the influence, the shared possibilities continue to vibrate within the field of our own being, often surfacing in the quiet, superpositional space of our dreams. Quantum mechanics is often seen as a cold, abstract, and counterintuitive theory, but when viewed through this metaphorical lens, it becomes a source of deep, spiritual wisdom. It tells us that we are more vast, more complex, and more mysterious than we can ever fully know. It tells us that our lives are a constant dance between the many and the one, between the infinite sea of possibility and the single, precious, collapsed reality of our lived experience. And it tells us that sleep is a sacred time, a nightly pilgrimage to the superpositional heart of our own soul, a time to remember the infinite possibilities from which we have come and to which we will one day return. The observer effect in quantum mechanics is more than just a statement about the influence of measurement on a physical system. It is a profound revelation about the participatory nature of the universe. It tells us that reality is not a static, pre-existing canvas that we passively observe. It is a dynamic, interactive process, a cosmic dialogue between the potential and the actual, a dialogue in which the observer is a crucial participant. The universe, in a very real sense, is a mirror. It reflects back to us the nature of our own inquiry. If we ask it a particle question, we get a particle answer. If we ask it a wave question, we get a wave answer. This does not mean that reality is purely subjective. that we can create anything we want simply by wishing for it. The underlying probabilities are still governed by the rigorous mathematical laws of the wave function. We cannot change the odds, but our choice of what to measure, our choice of which question to ask, is what collapses those odds into a definite outcome. We are the deciders. This has a powerful and direct parallel in the way we construct our own personal realities. The world we experience is not a raw, objective feed of sensory data. It is a filtered, interpreted and co-created reality, shaped by the questions we ask of it, the beliefs we hold about it, the attention we pay to it. If we look at the world through a lens of fear and scarcity, we will tend to observe and amplify the evidence that confirms that view. The world will, in a sense, collapse into a state that matches our observation. If we look at the world through a lens of compassion and abundance, we will tend to observe and amplify the evidence for that reality. Our gaze is not passive, it is creative. It is a cosmic act, and this act of creation is not limited to our waking lives. Sleep is a time when the nature of the observer shifts, from the conscious, externally focused ego to the deeper, more symbolic intelligence of the unconscious. In our dreams, we are both the creator of the dream world and the observer within it. The landscapes, the characters, the narratives of our dreams are a projection of our own inner state, our own fears, desires, and unresolved conflicts. But they are not just a passive reflection. The way we interact with the dream, the way we observe it from within, can change its course. In a lucid dream, where we become aware that we are dreaming, this power becomes explicit. We can consciously choose to confront the frightening monster, and in doing so, we may find that it transforms into a helpful guide. We can choose to fly, and in doing so, we collapse the wave function of the dream world in a way that makes flight possible. Lucid dreaming is a powerful training ground for the participatory nature of reality. It teaches us that our awareness is a creative force, that our intention can shape our experience. But even in ordinary dreams, this process is at play. The dream is a constant feedback loop between the unconscious observer and the dream world it is creating. It is a dialogue, a dance. The observer effect, at both the quantum and the psychological level, is a call to a greater sense of responsibility. If our gaze helps to create the world, then we have a responsibility to look with wisdom, with compassion, with courage. We are not just insignificant specks of dust in a vast, indifferent cosmos. We are the universe's own organs of perception, the points at which the infinite potential of the quantum vacuum collapses into the lived, experienced, and meaningful reality of a conscious world. And every night, in the quiet, dark theater of our own minds, we are given the chance to rehearse this sacred creative act, to practice the art of observation, and to remember that the universe is not just something we are in, but something we are doing. The uncertainty principle, with its fundamental limit on our knowledge, is not a statement of failure or imperfection. It is a description of the inherent dynamic and musical nature of reality. It tells us that the universe is not a static and machine-like system that can be perfectly known and predicted, but a fluid, vibrant, and endlessly creative process. The trade-off between position and momentum is not a flaw. It is the source of all stability and all change. It is what prevents the universe from collapsing into a state of perfect, static certainty. This principle, which governs the behavior of the smallest particles, is also a profound metaphor for the nature of our own minds and the process of living a creative and meaningful life. We often strive for certainty. We want to know the future, to control the outcome, to have a fixed and stable sense of who we are. We want to know both our precise position in life, our identity, our status, our place in the world, and our momentum, our direction, our purpose, our path forward. But the uncertainty principle suggests that this is an impossible and perhaps even undesirable goal. The more we try to fix our identity, to cling to a rigid sense of self, the more we lose our sense of direction, our capacity for movement and change. Our momentum becomes uncertain. We become stuck. Conversely, the more we focus on a single linear path forward, the more we can lose touch with our present reality, with the richness and complexity of our position in the here and now. We become ungrounded, disconnected. A healthy, creative life, like a stable quantum system, is a dance between these two poles. It is a process of finding a dynamic equilibrium between being and becoming, between rootedness and movement, between knowing who we are and being open to who we might become. Sleep is the nightly immersion into this dance of uncertainty. As we drift off, the controlling, certainty-seeking ego relinquishes its grip. We let go of our need to know, to define, to predict. We surrender to the unknown, and in this surrender, the mind is set free. Thoughts are no longer confined to a single logical track. They can move and associate in fluid and unpredictable ways. This is the state of hypnagogia, the creative, dreamlike state between waking and sleeping, a state that has been the source of inspiration for countless artists, scientists, and mystics. It is a state where the uncertainty is not a problem to be solved, but a space to be explored. In the dream state proper, this exploration becomes a full-blown symphony. The normal rules of logic, time, and space are suspended. We can be in multiple places at once. We can be different people. We can experience a reality that is built on the associative, poetic logic of the unconscious. This is not chaos. It is a different kind of order. An order based not on linear causality, but on emotional and symbolic resonance. It is the music of the mind, freed from the constraints of classical certainty. The uncertainty principle is not a pessimistic statement about the limits of our knowledge. It is a cosmic permission slip, an invitation to embrace the mystery, to dance with the unknown, to find peace not in the illusion of control, but in the wise and graceful surrender to the beautiful, unpredictable, and endlessly creative music of an uncertain universe. And every night, as we close our eyes and let go, we are attuning ourselves to this fundamental cosmic rhythm. The concept of the quantum vacuum, the idea that emptiness is not nothingness but a seething sea of potential, is perhaps the most profound and revolutionary insight of modern physics. It inverts our most basic, intuitive understanding of the world. We tend to think of things as being primary and space as being a secondary, passive container for those things. But quantum field theory tells us that the opposite is true. The field, the vacuum, the potential is primary. The things, the particles, the matter are secondary. Emergent phenomena, temporary ripples on the surface of this deep, energetic ocean. This is a worldview that has deep echoes in many of the world's mystical and philosophical traditions. The Buddhist concept of sunyata, or emptiness, for example, is not a nihilistic concept of non-existence. It is the understanding that all phenomena are devoid of any intrinsic, independent existence, that they are all interconnected and arise from a common, underlying ground of being, a ground that is often described as a luminous, creative void. The Tao Te Ching speaks of the Tao as the empty and unnamable source from which the 10,000 things arise. These ancient intuitions, born from deep contemplative inquiry, seem to be pointing towards the same fundamental truth that modern physics is now uncovering through the language of mathematics and experimentation, that at the heart of reality lies a creative, potent, and generative emptiness. Sleep is our nightly, personal journey into this creative void. As the external world of things fades away, as the internal world of thoughts and ego structures dissolves, we are left with the pure, undifferentiated potential of our own consciousness. This can, at first, feel like a frightening loss of self, a descent into darkness and nothingness. But if we can learn to trust this process, to surrender to this inner emptiness, we can find that it is not a void of non-being, but a womb of recreation. It is in this silent, empty space that the restorative and healing processes of the psyche take place. The fragmented parts of ourselves are integrated. The emotional wounds of the day are cleansed. The creative seeds of new ideas and new perspectives are sown. Dreams are the first sprouts that emerge from this fertile ground. They are the first forms that crystallize out of the formless potential of the unconscious. They are the virtual particles of the psyche, bubbling up from the inner quantum vacuum, giving us glimpses of the creative processes that are at work in the depths of our being. This understanding of emptiness as a creative potential can be a powerful antidote to the fear and anxiety that often accompany the dark, quiet, and empty spaces of our lives, both literally and metaphorically. The moments when we feel lost, when our old identity is crumbling, when the future seems like a blank, empty canvas, These are not just moments of crisis, they are also moments of immense creative potential. They are moments when we are closest to the quantum vacuum of our own being, the source from which all new realities can be born. To fall asleep is to practice this surrender, to consciously and willingly enter the creative void. It is an act of faith in the generative power of the unknown, an act of trust that from the deepest silence, a new and more beautiful music will emerge. The quantum vacuum is the universe's ultimate secret, and it is a secret that is not hidden in some distant galaxy, but is present here and now, in the space between our thoughts, in the silence between our breaths, and in the deep, dark, and wonderfully creative emptiness of our own sleep. The non-local connection of quantum entanglement, the spooky action at a distance that so troubled Einstein, is more than just a bizarre feature of the subatomic world. It is a fundamental statement about the nature of reality. It tells us that the universe is not a collection of separate, billiard ball-like objects that interact only through local forces. It is a single, indivisible, and holistic system, where the parts are so deeply interconnected that the concept of separation itself becomes an illusion. The two entangled photons, light years apart, are not two separate things. They are two aspects of a single, unified quantum state. To measure one is to measure the whole system. This profound unity is a truth that is often obscured by our classical, macroscopic experience, where things appear to be separate, distinct, and localized. But the quantum world reveals the deeper underlying reality of interconnectedness. This has powerful and beautiful implications for our understanding of ourselves and our relationships. We are not isolated islands of consciousness. We are entangled beings, connected to the people we love, to the natural world around us, and to the cosmos as a whole, through a web of invisible, non-local bonds. These connections are not just metaphorical, they may have a real physical basis in the quantum nature of our own being. The feeling of empathy, the ability to feel what another person is feeling, the strange synchronicity of thinking of someone just before they call, the deep, unspoken bond between a mother and her child. These are all experiences that defy a purely classical, mechanistic explanation. They hint at a deeper level of connection, a form of conscious entanglement that operates outside the normal constraints of space and time. Sleep is a state where we are particularly open to experiencing this entangled reality. As the conscious mind, with its focus on separation and individuality, quiets down, the deeper, more holistic intelligence of the unconscious comes to the fore. In our dreams, the boundaries between self and other often dissolve. We can merge with other people. We can become animals or objects. We can experience a reality from a perspective that is not our own. We can have vivid, emotionally resonant dreams about people we are deeply connected to, even if they are far away. These are not just psychological phenomena. They may be the subjective experience of our own, real, quantum entanglement with the world. They are moments when our consciousness taps into the underlying unity of the cosmos, the single wave function that describes all of reality. This perspective can bring a profound sense of comfort and meaning. It tells us that we are never truly alone. Even in our most solitary moments, we are part of a vast, interconnected web of existence. The people we have loved and lost are not gone in an absolute sense. The entanglement, the connection, the shared information persists in the quantum field of the universe and can still be accessed in the non-local realm of our dreams. Quantum entanglement is the universe's most beautiful and mysterious secret. It is the physical basis for the spiritual truth that we are all one. And every night, as we surrender to the mystery of sleep, as we let go of our sense of a separate self and dissolve into the dream sea of the unconscious, we are returning home to this fundamental, entangled unity. We are remembering, at the deepest level of our being, that we are not just in the universe, but that we are the universe experiencing itself, connecting with itself, and dreaming of itself. The dual nature of light, its ability to be both a continuous, spreading wave and a discrete, localized particle, is not a contradiction. It is a paradox that reveals the deep, complementary nature of reality. The principle of complementarity, first articulated by Niels Bohr, states that these two aspects of reality, the wave and the particle, are mutually exclusive, yet both are necessary for a complete description of the phenomenon. You cannot see both aspects at the same time. but you need both to understand the whole. The choice of experiment determines which face of reality is revealed. This is a profound philosophical insight that extends far beyond the realm of physics. It suggests that reality is not a single, monolithic thing, but a dynamic interplay of opposing, yet complementary, principles. We see this duality everywhere in our own lives: light and shadow, order and chaos, being and becoming, masculine and feminine, conscious and unconscious. A full, integrated life is not about choosing one and rejecting the other. It is about learning to hold the tension between these opposites, to dance with the paradox. And nowhere is this dance more apparent than in the daily rhythm of our own consciousness. Our waking life is the particle aspect of our being. We are focused, localized, and goal-oriented. We interact with the world as separate, discrete individuals. We operate in the realm of linear time, of cause and effect, of either-or logic. Our consciousness is like a focused beam of light, illuminating a single point of reality, but our sleeping life is the wave aspect of our being. The focused, particle-like ego dissolves, and our consciousness spreads out, becoming a diffuse to non-local field of awareness. We are no longer bound by the constraints of linear time or a single identity. We operate in the realm of myth, of symbol, of both and logic. Our consciousness is like a spreading wave, interfering with itself, creating complex patterns of meaning and emotion. These two states of being, the waking and the sleeping, the particle and the wave, are not opposed to each other. They are complementary. They are two essential parts of a single, whole human experience. The waking life provides the structure, the action, the engagement with the world. The sleeping life provides the context, the meaning, the connection to the deep, underlying currents of the psyche and the cosmos. Without the focused action of the particle, the wave remains a field of unmanifested potential. Without the deep, integrative wisdom of the wave, the particle becomes a disconnected, meaningless point. We need both. The health of our psyche depends on the graceful, rhythmic oscillation between these two modes of being. To honor our sleep, to value our dreams, is to honor the wave-like aspect of our own nature. It is to recognize that we are not just the solid, definite things we appear to be in the light of day, but also the fluid, mysterious, and infinitely interconnected waves we become in the darkness of the night. The wave-particle duality is not just a paradox of physics, it is the fundamental rhythm of life itself, a rhythm that we are privileged to experience in the most profound and personal way. Every time we close our eyes and surrender to the gentle, wave-like embrace of sleep, the incessant, energetic hum of the quantum vacuum, the constant bubbling of virtual particles in the midst of silence, is not a flaw in the universe's design. It is the very engine of its creativity. The void is not a static backdrop. It is a dynamic, living presence, a field of pure potential from which all forms arise and to which all forms return. This is a vision of the cosmos that is not mechanical and deterministic, but organic, spontaneous, and endlessly generative. The whispers of the vacuum are the first stirrings of existence, the premonitions of a universe waiting to be born. This understanding has a powerful and transformative echo in our own inner lives. The silent spaces of our own consciousness, the moments between thoughts, the pauses in conversation, the quiet stillness of meditation, the deep emptiness of sleep are not voids of non-existence. They are the most fertile ground for our own creativity, our own healing, our own transformation. We live in a world that is terrified of silence, of emptiness. We fill every moment with noise, with distraction, with activity. We are afraid that if we stop, if we become still, we will be confronted with a terrifying nothingness. But quantum physics, and the wisdom of the contemplative traditions, tells us that the opposite is true. It is in the silence that we can finally hear the subtle music of our own being. It is in the emptiness that we can touch the source of all our creativity. Sleep is our nightly, mandatory pilgrimage to this inner sacred silence. As the noise of the day's events and the chatter of the conscious mind subside, we are given the chance to connect with the deep, quiet, generative vacuum of our own psyche. In this state, the mind is not passive, it is incredibly active, but in a different way. It is not engaged in the linear, logical processing of the waking state, but in the holistic, associative, and integrative work of the unconscious. It is in this inner silence that the fragments of our experience are woven into meaningful narratives. It is here that emotional wounds are processed and healed. It is from this fertile emptiness that the seeds of new ideas, new insights, and new solutions to our problems can spontaneously emerge. A dream is a virtual particle born from the vacuum of the mind. It is a fleeting, symbolic expression of the deep, creative processes that are at work in our inner silence. Sometimes these dreams are like the soft whispers of a gentle emotion. Other times they are like the powerful, transformative roar of a deep, archetypal insight, but they all arise from the same source, the potent, creative, and endlessly mysterious emptiness that lies at the heart of our own being. To learn to value silence, to befriend our own inner emptiness, to trust in the wisdom of our own sleep, this is to align ourselves with the most fundamental creative principle of the universe. It is to understand that all true creation, whether of a galaxy, a work of art, or a new and more integrated self, is born not from frantic effort, but from a deep and patient listening to the silent, secret, and life-giving whispers of the void. The quantum nature of time, its refusal to be a simple, linear, and absolute flow, is one of the most profound and mind-altering implications of modern physics. It suggests that our everyday experience of time as a river carrying us inexorably from a fixed past to an open future is a powerful, but ultimately limited, human construction. At the fundamental level, the distinction between past, present, and future may be far more fluid and interconnected than our classical intuition allows. The phenomenon of retrocausality, or backward-in-time influence, which has been tentatively explored in some quantum experiments like the delayed choice quantum eraser, suggests that a choice made in the future can influence the state of a system in the past. This is not to say that we can send messages back in time to change history in the classical sense, but it does suggest that the relationship between cause and effect is not as straightforward as we assume. The universe may be a block of space-time, as Einstein's relativity suggests, where past, present, and future all exist simultaneously, and the flow of time is an illusion of our consciousness. Or it may be a probabilistic branching structure, where the future is a set of open potentials that can retroactively influence the path that was taken to get there. Whatever the ultimate picture, the quantum world tells us that time is not a rigid container, but a dynamic and participatory process. And nowhere do we experience this dynamic, quantum nature of time more directly than in our dreams. Sleep is a realm where the linear chronological time of the waking world is completely abandoned. A dream can span decades in a matter of minutes. A moment of intense emotion can feel like an eternity. We can seamlessly transition from a vivid memory of our childhood to a fantastical vision of a distant future. The past is not a fixed record. It is a living, malleable presence that can be re-experienced, reinterpreted, and even healed. A dream can take a traumatic memory from the past and recontextualize it, allowing us to find a new meaning, a new resolution that was not available to our waking mind. The future is not a distant, unreachable shore. It is a field of potential that we can explore and interact with. A dream can present us with a symbolic preview of a challenge we are about to face, or offer an intuitive solution to a problem that has been troubling us. In the dream state, our consciousness is not a passenger on the river of time. It is the river itself. It can flow forwards, backwards, sideways. It can create eddies of memory, rapids of emotion, and deep, still pools of timeless insight. This is not just a psychological curiosity. It may be a direct, subjective experience of the fundamental, quantum nature of time itself. Our brains, as quantum biological systems, may be uniquely attuned to the nonlinear, probabilistic, and interconnected structure of space-time. To sleep is to step outside of the illusion of linear time and to enter into a more fundamental, more real relationship with the temporal fabric of the cosmos. It is a nightly reminder that the past is not gone, the future is not set, and the present moment is a point of creative potential where all times meet. The dreams we have are not just stories we tell ourselves, they are our soul's way of navigating the deep, mysterious, and beautifully quantum ocean of time. The existence of a multiverse, a vast, perhaps infinite ensemble of parallel universes, is one of the most extraordinary and mind-bending ideas to emerge from modern theoretical physics. It is not a single theory, but a consequence of several different lines of inquiry, from the many worlds interpretation of quantum mechanics to the theory of eternal cosmic inflation. In the many worlds picture, every quantum measurement, every probabilistic event causes the universe to split into multiple branches, one for each possible outcome. There is a universe where the atom in Schrödinger's box decayed, and a universe where it did not. There is a universe where you turned left at the intersection this morning, and a universe where you turned right. Every choice, every chance creates a new world. In the eternal inflation picture, our universe is just one bubble that nucleated from a vast, eternally expanding quantum vacuum, and other bubble universes, potentially with different physical laws and constants, are constantly being formed. This is a vision of reality that is almost incomprehensibly vast and rich. It suggests that our entire observable universe, with its billions of galaxies and trillions of stars, is just one grain of sand on an infinite cosmic beach. While we can never, even in principle, directly observe or communicate with these other universes, the idea that they exist has a profound impact on our understanding of our own. It provides a potential solution to the fine-tuning problem, and it forces us to confront the true scale of reality. But could we, perhaps, have an indirect connection to these other worlds? Could there be a subtle leakage of information? A faint echo from these parallel realities that we can perceive? This is where the nature of dreams becomes a fascinating area for speculation. Dreams are a realm where the impossible becomes possible, where the logic of our waking reality is suspended. We can encounter people we have never met, but feel a deep sense of familiarity with them. We can visit places that do not exist on any map, but which feel as real as our own home. We can experience lives that are not our own, with different histories, different relationships, different identities. Could it be that in the deep, non-local state of dream consciousness, our minds are capable of tapping into the universal wave function, the vast superpositional state that contains all of these parallel realities? Could a dream be a glimpse, a fleeting, symbolic echo of the life of an alternative self in a parallel universe? This is, of course, a highly speculative and unprovable idea, but it is a beautiful and compelling one. It would explain the profound sense of otherness and yet familiarity that so many dreams possess. It would account for the seemingly infinite creativity and novelty of the dream world. It would suggest that our consciousness is not confined to this single, collapsed reality, but has a deeper connection to the vast multiverse of possibility. In this view, sleep is not just a journey into our own personal unconscious, it is a journey into the cosmic unconscious, a nightly exploration of the infinite library of what could be, and what, in some other corner of the multiverse, actually is. To dream is to be a cosmic explorer, a traveler between worlds. And every morning, when we wake up, we return to our own, the specific branch of reality, perhaps carrying with us a faint, dreamlike memory of the other lives we are living, the other choices we have made, the other stories that are being told in the grand, and perhaps infinite, book of the cosmos. The ultimate mystery that the quantum world presents us with is the mystery of consciousness itself. As we have seen, the observer is not a passive bystander in the quantum drama, but a central and enigmatic character. The very act of observation seems to be what transforms the ghostly, probabilistic world of quantum potential into the solid, definite world of our classical experience. This has led some of the most profound thinkers in physics, from Schrödinger and Bohr to more contemporary figures like John Wheeler and Roger Penrose, to conclude that we will never have a complete theory of the universe until we have a theory of consciousness. The two are not separate problems, they are two sides of the same, deep mystery. The hard problem of consciousness, the question of how and why a physical system like the brain gives rise to the subjective, qualitative experience of being, the feeling of redness, the sound of a C sharp. The feeling of love is perhaps the greatest unsolved problem in all of science. The classical mechanistic view of the brain as a complex biological computer has so far failed to provide a satisfactory answer. It can explain how the brain processes information, but not how it produces experience. This is where the quantum world offers a new, and perhaps more promising, avenue of inquiry. The quantum realm is not just about smallness, it is about a different kind of reality. A reality of holism, of interconnectedness, of non-locality, of unmanifested potential. These are properties that seem to resonate more closely with the nature of our own inner experience than the classical world of separate, solid objects. Perhaps consciousness is not an emergent property of classical computation in the brain, but is a fundamental the quantum phenomenon. Perhaps the brain is not a classical computer, but a quantum one, a biological instrument that has evolved to harness the strange and powerful properties of the quantum world to create the symphony of our subjective experience. In this view, the brain is not the source of consciousness. It is the receiver, the antenna that attunes itself to a more fundamental universal field of consciousness that pervades the entire universe. This would be a return, in a new, scientific guise, to some of the oldest ideas in human philosophy, the idea of a world soul or an anima mundi. Consciousness is not something that we have, it is something that we are, a localized expression of a cosmic principle. And sleep would be the state in which our individual, localized consciousness returns to and merges with this universal field. In the deep, dreamless state of slow-wave sleep, the ego dissolves, the sense of a separate self vanishes, and we are left with a state of pure, contentless awareness. This may be the closest we can come in our human experience to touching the ground state of consciousness itself, the quantum vacuum of the mind. And from this state, as we transition into the REM sleep of dreaming, new forms, new images, new narratives arise, like virtual particles bubbling up from the void. Dreams are the universe's way of exploring its own, infinite imaginative potential through the unique individual lens of our own consciousness. This is a vision of reality that is both scientifically radical and spiritually profound. It suggests that our quest to understand the universe and our quest to understand ourselves are not two separate journeys, but one. The secrets of the cosmos are not just hidden in the hearts of distant stars or in the equations of theoretical physics. They are also hidden in the deep, silent, and mysterious nature of our own conscious awareness. To study the quantum world is to study the mind of God, as Einstein once said, and to study our own consciousness, to explore the depths of our own sleep and dreams, may be the most direct path we have to understanding the deep, quantum magic that underlies all of existence. The universe is not a dead, mechanical thing that happens to contain pockets of consciousness. The universe, at its most fundamental level, may be consciousness, and we are the dreams it is dreaming.